wouldn't.
Yeah, maybe. You guys.
No, I know. I keep on the. Okay, everyone. Good morning. Let's take our seats. And welcome to the Thursday session. So, the first speaker of today is Hermano Belden, and he's going to talk on a critical view of modified gravity cosmologies beyond lava CDM.
Okay, thanks, Emmanuel. Thanks, Giovanni, for the kind invitation. It's been a great pleasure to be here. So, not my first time in Chile, but first time in this Chilean latitude. It's very nice here. And so, maybe I'm not going to be so critical as I was, my title is supposed to be. But the point is, I decided to prepare a talk thinking on a more broad audience, including students and people, even senior researchers not so familiar with cosmology, instead of a very specialized talk on a very specific paper. So I'm sorry for the colleagues that were 2 months ago in Bahia. So we had the Cosmos Sul, when we stay in Brazil, Cosmos Sur, and the rest of South America. So that was a very nice meeting, very nice to meet all the South American community time by time. So, and for the ones, Susanna, Joel, and were there, sorry, it's very similar talk, but anyway, I hope you enjoy again. Okay, so just to give you a few tips, the place I'm from, because I'm always saying I'm from Ouro Preto, and people, where is it? And so Brazil is quite large, you know. So there is a little map of Brazil here, and this red region highlights this state, Minas Gerais, and this point, this red point here, is where the city is located. So Rio de Janeiro is here, São Paulo here, so Vitória, this point, and so you see it. So we are talking about 500 kilometers each from to the coast here. And it's a very historical city, so all the gold, going out from Brazil during the 17th and 18th century came from this region. And so it's also quite interesting because, so this is one of the first universities in Brazil, this building here, and they had an astronomy department there because engineers, they didn't have GPS at that time, and they had to build the cards putting the coordinates by observing the stars, and so that was one of the motivations to start astronomy in that place here. Okay, let me go to the content of this talk. So what I'm going to talk here is maybe very general thoughts on how can we explain only the background cosmological evolution, okay? Just a little bit we'll talk about the perturbations, but the focus is on the late time cosmology, okay? So, and of course we have the lambda CDM model that works quite fine for this, to explain this data. But yeah, we also can use modified gravity cosmologies to explain that. And I will tell you why we should go to this modified gravity sector and what are the motivations behind them. And then at the end, I will focus only on two specific models I have worked in the last couple of years. So this one here is the f of RTT. Here is not the torsion scalar, is the trace of the energy momentum tensor. And also the unimodular gravity. Just two examples at the end of my talk. Okay, so when I was organizing this talk, by what I had in mind was maybe two ambitions to try to answer some questions, but so quite, maybe quite ambitious questions. For sure we don't have this answer now, but so can we eliminate the need for the dark sector of the universe? So by dark sector, I mean dark matter and dark energy, as you know. And yeah, it would be nice to eliminate them, to explain what is going on with astrophysical and cosmological data without these components, but so. So do we have a final word on whether or not modified gravity really works at cosmological level? I don't know your own opinion, but my aim here is try to give an answer to that. So is there a single modified gravity model that explains both astrophysical and cosmological data? So it's nice when you have a modified gravity model that explains so cosmological data or astrophysical data, but of course we have to explain both at the same time. So maybe I might be wrong, but I think that the answer is still no. I mean, we still have difficulties in finding one specific modified gravity scenario that explains everything at the same time. So as you know, the standard theory is general relativity, more than 100 years old. This is quite, so if you open any newspaper at that time, people knew what is meaning, what is behind these symbols here in the 20s, last century. I have the feeling that today it would be not the same situation. If you publish in the newspaper these equations, what is going on behind that? But anyway, so this is quite maybe too light here, but this is a quite old picture, but showing that general relativity has passed all the tests it has been tried in the last century. So, since the original tests proposed by Einstein, the classical tests of general relativity, but also with pulsars, all the black hole physics, and more recently with the detection, the direct detection of gravitational waves. It's a great confirmation of GR predictions. This supported the Nobel Prize almost 10 years ago. It's quite fast. And so the point is then there is no reason to doubt on general relativity. And so since we trust a lot on general relativity, we try then to explain the universe using this theory. And this history is also quite old, 102 years old. This is the original paper by Friedman, 1922. This is the one I sent you, Susanna, this morning. So this is the first time that the famous Friedman equations appear in the literature. So here you have them. So this is the scalar, the expansion scalar. So written in terms of the density and the curvature. So you can combine these equations and find an equation for the acceleration. And depending on your budget, energy budget content here, you can have many different solutions. You can start with, of course, we start with the singularity, and then the expansion is quite natural, but the future depends on this content. So we are right now approaching a situation in which, so we know, so the standard cosmological model is quite known. I show you this picture later on, what means this standard cosmological model, but the point is, what is the challenge now? So, okay, we have a theory to explain this cosmological expansion, but then we have to tie all the different observational pieces to this theory. And where these observational sources come from. So we have at least 4 different moments or regions in time. Of course, we can observe the current universe locally. So we map locally structures and local expansion, and we have an idea about how the universe is expanding. So then we start to make like a tomography of the universe. We go deeper and deeper and deeper with sky surveys. And then we start mapping the universe along its evolution. So then we also have a very important snapshot from the beginning of the universe, which is the CMB. This happened around 380,000 years after the Big Bang. And we also have information about the primordial nucleosynthesis, the first process of nuclear reactions giving rise to helium, hydrogen, helium, lithium, beryllium. And these traces of these elements also tell us about the expansion rate at that time. So then when we tie all these pieces together, we can have an idea about the entire evolution of the universe. So then we reach to what we call the standard cosmological model. This is, of course, a combination of both theoretical and observational sides. On the theoretical side, of course, we assume the cosmological principle, which means that the universe is homogeneous and isotropic on large scales. This really facilitates a lot. Yeah, we can talk a lot what are the ideas and the assumptions behind this cosmological principle, how we deal with that, but so. We also...
There is an observational hint.
Yeah, this is yeah, based on observations, for sure, yeah. But before to confirm this with observations, we assume as a theoretical assumption. Of course, GR, we have to start with the theory to describe the gravitational interaction. And we also assume that all the matter content, the energy content of the universe behaves as a perfect fluid, which can also be seen as a very strong assumption. If you go to kinetic theory physicists, they have strong claims against this assumption. But anyway, all these assumptions make all the job quite simple. On the observational side we have the Hubble-Lemaitre law, formerly known just as the Hubble law. So we have the CMB, we have the Big Bang nucleosynthesis, at least. Of course, we can add more and more and more purple things here, but anyway, these are the basic ones. And then we have a minimum setup to construct how the universe has evolved in the last billions and years. And that's a point. How many billion years what is the age of the universe? This is, of course, a very interesting question. So the point is, a part of this observational things, we also have astrophysical and cosmological evidence on the existence of dark matter. So dark matter is supposedly matter, like normal matter. It understands the gravitational interaction, but it's not taking, this candidate is not enrolled in electromagnetic courses. It doesn't understand the electromagnetic sector, so we cannot observe it directly. So there is no emission from this component. So when we observe then, and then the entire history, so it started like 90 years ago with Zwicky, this guy observing the coma clusters. So he was observing this these very rich galaxy clusters, and observing that the dispersion velocities were too high for the visible matter there, and then he had to suppose that, okay, maybe we have a lot of matter there. So we also have observations from collisions of galaxy clusters and rotation curves in galaxies. So you see this flat behavior is a typical evidence on the existence of dark matter in these structures. We also have evidence on dark matter in our inner Milky Way. So then dark matter is really everywhere. So on the cosmological side, we can understand the process of structure formation only if you add dark matter. So dark matter should be formed, should be there even before the CMB radiation is set free, and then baryons are starting to form structures. So this is illustrating what I'm telling here. So when when the hydrogen is forming the first hydrogen clouds, so we have to have some preforming structures, even linear structures, but to accelerate the clustering of structures, dark matter structures. So then we can explain the existence of nonlinear structures today, like galaxies and galaxies clusters, only if we admit this pre-existence of dark matter formation process in the universe. So this is a quite strong argument in favor of dark matter. So you know quite well that we also have this dark energy phenomena. The point is, we know that the universe is accelerating, okay? It's not only expanding, but expanding in an accelerated way. We know this already, so since the end of 90s. This started with the observation of supernovae type 1a. This is one single observation, one single supernovae in a galaxy. And so this gave rise to the Nobel Prize in the 2011 to this discovery, and now it's a very common thing in cosmology. You cannot discuss cosmology today without talking about dark energy. But the point is, there is no doubt that the universe is really accelerating. The point is not that we have a model like the lambda CDM that fits the data very well, and then because lambda is there, this means that the universe is accelerating. So this is one work we did some years ago. It started with these ideas here by Marina Zeichel and Dominic Schwartz in these papers. So then we did this analysis again with more recent data. So the point is, we don't have to take a model and fit data with this model and to see that, okay, the preferred space parameters of this model corresponds to acceleration. No, let's ask if the data itself tells you that the universe is accelerating. So we are not assuming any model, just asking if, okay, let's say that the universe never accelerated. Can you refuse it? And the point is, the data tells you that yes, with a very high confidence level, we can refuse this, the statement that the universe never accelerated. So this means, yes, it's been in accelerated phase, independent on the model we choose to explain it. Okay, we can also ask about another very simple question. So is the universe old enough to accommodate the structures it has? This has been, during the last century, a very common question. The point is, what is the age of such structures? So, and then the astrophysicists, they have very strong claims, and they are doing that for decades, to show that the globular clusters, they are quite old objects. So the last estimation, at least I know, is from 2021, from this paper here by Valsin. So are they claiming that there are probably structures in the universe as old as 14.16 giga-years. And this means that the universe cannot be younger than that. So the point is, how in the standard lambda CDM model, the age depends on the quantity of dark energy. And we know that, yeah, so this is the age of the universe in giga-years. So this line, and here we have the quantity of dark energy. So this is a flat model. So this blue line here, so if you have only 20% of dark energy today in the cosmological constant form, the universe would be around 10 gigayears. So more dark energy, the more dark energy we have, the older the universe is. So this means this pushes the quantity of dark energy to higher and higher values. This means that we really need a considerable amount of dark energy to explain at least the age of the universe. So again, this is a quite simple argument in favor of, so this blue stripe is not so updated as this red line here I took from this reference. Okay, so then finally when we put all these pieces together, we find the so-called concordance models. So it's, if you Google it, cosmology, Big Bang theory, and not Big Bang theory to be the show, but if you Google Big Bang cosmology, you see these pictures, and so the picture is, we know quite well. Only 5% of the universe is made of no matter, and then we have around 25% of dark matter and 70% of dark energy. Okay, the point is we have no direct evidence of such dark components. So we still don't have a direct measurement of them. Okay, it's not true that this percentage, when we say, the universe is made of 25% of dark matter, 70% of dark energy. We have to have in mind that these relations, they change in time. So this is the scenario today, but if you go back in time, the universe was, for example, this pizza-like diagram here. When we see it around the CMB release, we had a different constitution. So, of course, dark energy was not important at that time. It's really a recent phenomenon. It's really a component that is arising very close to us. Not so close. If you think about on cosmological time, cosmic time, so the dark energy started to dominate like 3.5 billion years ago. In terms of the redshift, it's a very small number. This gives rise to that coincidence problem discussion, but when we think about the cosmic time, the situation is quite different. Okay, so then why I'm introducing these pizza-like diagrams, because now I want to give you a motivation for the discussion is coming in the next slide. So it's not nice as physicists to say that we work as cosmologists, we work with something that, so 95% of the universe is the topic we work with. When you go to ask jobs to other physicists, they make jokes. Come on, at least I can go to the lab and try things that I'm seeing. And you work with things that you are not observing. But anyway, so then if you try to replace the existence of this dark sector by some modified gravity theory. So this would be the first attempt. So the point is, let's say that either dark energy or dark matter is replaced by modified gravity. Okay, maybe dark matter really exists, but dark energy is an effect of some manifestation of modified gravity on large scales. So this would give rise to this kind of pizza-like diagram. So we still have baryons, we still have dark matter, and so this, of course, today's values. And a huge part would be geometry. Okay, but then we still have a missing piece here. So what would be really nice, and sometimes we really look for it, is to replace all the dark sector by modified gravity. This means that the same 5% of the universe would be made by baryons, but the remaining 95% by geometry. That sounds great. Then we solved like two puzzles with one single idea. So, but maybe the life's not so simple. And we always try to be economic when we do things, but maybe the reality is more expensive than we expect. So perhaps we still have to have the dark matter sector, the dark energy sector, and on the top of that we still have some modified gravity. So this would be quite expensive, but sometimes it's the price to pay. So this is not a standard picture, a standard procedure in literature, but perhaps we are going to focus on this kind of models more and more. So why? Because when we test all these GR-based cosmologies with dark energy models, so by dark energy models, not only the cosmological constant one, but we have these parametrizations in which the dark energy equation of state changes in time. So, and we take all these concordance samples. I mean, by concordance samples, I mean all this observational data that tells us that the lambda CDM is the preferred one. Basically, all the. So then we are trying to constrain these models, and we always find that lambda CDM is a very nice picture. So maybe the point. So this changed some months ago with the DESI results. You, at least up to my knowledge, it's the first time that you have a set, observational data set, that is telling you that lambda CDM is quite far from the preferred model parameters. So if here what we have is a constant equation of state parameter for dark energy, -1, of course, is lambda. This is okay. But then when we go to the CPL parametrization, where the dark energy equation of state changes in time. So this is omega naught and omega A. So this would indicate the time variation of dark energy. So 0 here would be consistent with a constant parameter, and -1. So lambda CDM is this point here. So then you see that the contours are really a bit far from this point here. So maybe it's an indication that we are, of course, we cannot be so, so this is the final word. Yeah, we finally found that dark energy is a time-varying component, but it's a first indication. Okay, so then when we go to modified gravity scenarios, and then we have these nice pictures by, so Emmanuel, so this is a book, this cantata network. So it's almost impossible to track in the literature all the different modified gravity scenarios and how they deal with the cosmological data. So I hope it's going to be clear with the next slides, because if you just add new fields, like, so all the tensor, vector, and scalar sector, so you see some of them, most of the possibilities here. Later on, I will talk about Hondesky classes, but so you see that you have groups working only in each of these blue pieces here. So then we can also modify gravity, adding invariants. So you have at least these 10 different options here. Later on, I will talk a bit about these meta couplings here. So we can also try to modify gravity, having in mind how the quantum version of a modified gravity theory would look like. And you have all these possibilities. And you can also change geometry. So, and then let's see that you have understood all these different possibilities, and at the end of the day, as you read in this paper, you go back to the principle. So the last reference in this book is Aristotle. This means that you go back and try to understand again, if you really, so after you wrote 2,291 references, you realize that you have to start from the beginning again. But okay. Okay, so what about testing modified gravity? And of course, usually modified gravity has the GR limit, the lambda CDM, the GR plus lambda limit. We saw 2 days ago one lecture on F of R. This Husawiki, this Sarobinsky models, they have the lambda CDM limits. Susanna showed us that. So usually we start with the lambda CDM model because it's this point belongs to the modified gravity. It's there. Okay, but then when we try now this, this is one of the recent attempts to see how this new DESI data would work with modified gravity series. It's a bit also, in this representation, it's a bit out of the lambda CDM. So what is this? Later on, I will talk about this Horndeski series, but in terms of this EFT, effective field series for dark energy, this means that we can switch on several different Lagrangians in our series, like L2, L3, L4, L5. So then, let's say that lambda CDM is here, and as we switch on new couplings, we add new parameters and new degrees of freedom. And so, if lambda CDM here, we have like the Brans-Dicke line, so we can be over the simple Brans-Dicke series, and we can recover lambda CDM. We also can switch on more terms like G3, L3, and we would add a new plane in this space. We can add switch on 4 and 5, and then we have more and more possibilities to build a new modified gravity series. So the point is, at least from this paper here, the modified gravity models indicates a preference over lambda CDM at 2.4 sigma level. We conclude that modified gravity offers a viable physical explanation for DESI's preference for evolving dark energy. So this means then, since we can have modified gravity models that map into an evolving dark energy component, if evolving dark energy components are preferred with DESI data, this should be the same with modified gravity. Okay, so we did that 5 years ago with Guilherme Brando. He's now at CBPF, Felipe also, and Eric Linde. So we tried exactly this. So let's see that we have modified gravity, and this means that we have an evolving background, a time-dependent dark energy-like background, parameterized here in terms of this WA and W naught. So then what we found at that time is actually all this region is unstable. So we were like anticipating that it's quite difficult to explain modified cosmological background data in terms of modified gravity, in terms of these parameterizations here. So now we should compare with this instability, unstable region with the new DESI data as I showed you in the last slide. Okay, so now let me enter in this second part of my talk where I'm going to talk you a bit about more specific models. So maybe we should be, as I told you, from all those possibilities about how to modify gravity, one of them is to introduce these meta-coupling terms. Here you see that T is a trace of the energy momentum tensor, and if this is put here inside your gravitational Lagrangian, so this gives rise to a new kind of theory. You can test it. This is proposed 2011 by Tiberio, Francisco, Shinji, and Sergei Odisov. It's a quite famous approach to deal with these meta-coupling sectors. So one very nice characteristic feature of the theory is that this is a non-conservative theory. So for divergence of the energy momentum tensor doesn't vanish. So if, of course, you can find a combination of these things here that makes you, that goes to 0, and then you have a conservative theory, but in general it doesn't. Okay, so we did this works recently on this theory, trying to see, okay, can we explain the observational data with theory? Of course, we are not the only group doing that, but this, I'm going to show now some of the results with this. Okay, We start picking a specific form of this function here. Of course, we keep R linear because then we are close to GR and we are adding something. So we are not going to do f of R like different dependence on the rich scalar. Let's keep GR, but we add this part of GR, but then we add some polynomials and to this Lagrangian here. So this would be how the expansion looks like. The point is that the omega, the energy density parameter, the fractionary one, does not belong to the usual conservation law. So the right-hand side is not 0. We have to solve it numerically, and then we put there in the expansion, and then we see how it looks like. But what is nice here is that in this theory, this is quite simple, because when we look at this relation here, if we do as we do in lambda CDM, there is an extra constraint in the parameters that when we set them to today's values, so we see a relation between the parameters, and then we can eliminate one parameter in some sense. So then this constraint applies between the amount of the matter fields and the modified gravity parameters here, like lambda and gamma. So we cannot do the same in f of r because f of r is not linear in general. So when we write down the expansion, modify the Friedmann equation in f of r, this depends on the derivative of the density. Then we cannot set the same constraint. And then we usually go to these numerical strategies as Susanna showed us. Okay, and then what we did 2017 was to show that these models, they really have difficulties to explain minimal, at least this cosmic chronometers data. I mean, this is a very qualitative analysis. We could easily see that they cannot fit at least this data. So then we should not go on with them. So more recently, we tried to expand this analysis by including more data, also to including this exponential term here. So we have, again, the expansion rate in terms of the density and the modified gravity parameters here, like alpha beta and gamma n. So we again have this constraint, and we try to ask, okay, let's see minimum requirements for this model. So let's see if this model can minimally explain at least 3 observational facts. So again, the universe cannot be so young. It should be at least older than 14.16 gigayears. This is a fair requirement. So when we go to this gas mass fraction in galaxy clusters, there is this constraints that the omega matter is around 0.3. And then we should ask ourselves here, what is the meaning when we go to modified gravity and we have a matter density? What is the meaning of that matter density in modified gravity compared to the matter density in GR? I mean, when we say that, let me go back to here. So is this omega the same as the matter parameter in lambda CDM? Because these constraints on the gas mass fractions, they around 0.3, omega 0.3. So they have in mind that you are summing up baryons and dark matter, and so this means that you have, in some sense, the entire expansion except the dark energy sector. Okay, so then we have to put an extra discussion here on what is the meaning of the matter density parameter in modified gravity series. And okay, of course, all these 2 criteria should be within at least the 3 sigma contours of observational data like supernovae, age of Z. Okay, this is what we found. Let's take this simple example here of a polynomial form. Just a comment here. Of course, you can see this kind of theory as GR plus an effective fluid. I mean, you always can do this trick to take this extra geometrical contribution here to send to the right-hand side of your equations and say that at the end of the day you have GR plus matter and some effective modified gravity fluid. Okay, just to keep you in mind about these results. That's why we still have the lambda CDM limit here. So if you put n 0, this is just a Lagrangian with r plus a constant. This is lambda CDM. Okay, so then what we did. So these dotted lines are the age contours. So here is the n parameter and the gamma bar. These red lines here are the limits of these gas mass fraction parameters from galaxy clusters. So this means that you have to be between the red lines. We have to be above this dotted line. And when you use supernovae and age of Z and BAO data, these are the contours. Then this means that only this region here survives. Yeah, and of course, the lambda CDM is there. So this parameter 1.4 is like twice omega lambda.
So in the end, you have the standard matter Lagrangian. So apart from this FOR, T, you have
plus a meta Lagrangian, yeah.
So in this case, lambda CDM corresponds to n equals
0.
0.
Yes.
But then
here.
Yeah, but why then you were saying that lambda CDM is up there, 1.4?
No, because when we map this quantity here into omega lambda, this is 2 times omega lambda. Because here I had this
yes.
Yeah.
It's a different thing.
Okay. So this is for this polynomial model. For the exponential one, again, if beta is 0, it's the same situation. We are close to lambda CDM. And the concordance lambda CDM model is here, okay? And the same requirements. We should be above the age line. We should be between the red lines. And we have to be within this 3 sigma contours. And this is the region that still survives here. Okay, so then we did recently to the perturbations of these models. And we take the same model, we identify what is really matter in the series, and then we calculate the first order perturbation equation for the density contrast. So it's quite, you see that it's not so, it's quite trivial to see that if you kill all the modified gravity terms, then this C bar is 1. So then F returns to 1 as well, and G to 1 as well. And then we cover the standard. This is a conformal time derivative, okay? And age, this calligraphic age as well, this in terms of the conformal time. So then this is the equation we find when we make scalar perturbations in this model. And this is what we did found with the F sigma H data. They kind of oscillate a bit, but it's at least here we are just trying to see only the qualitative results. We didn't try any statistical analysis with this data. Okay, just to finish my presentation, yeah. So let me move on to a different scenario we were analyzing more recently. This is even more radical because we were studying unimodular gravity. And as you might know, so there is a famous and quite usual claim that, okay, unimodular gravity is exactly GR plus cosmological constant. But this cosmological constant appears in unimodular gravity as an integration constant. Okay, we have an explanation for that. So then this means that both models are exactly the same. They are equivalent. But why they are equivalent? Because usually you assume the conservation of the energy momentum tensor. And this is the reason why in unimodular gravity this cosmological integration constant appears. But what we did here is, no, let's say that we are not putting this extra constraint. And okay, then we, of course, have a different equations, dynamical equations. These are the Friedman modified Friedman-like equations, and at the end, we saw that, of course, we still have a degree of freedom, which is the equation of state. But what is nice is that the dynamics age depends on the enthalpy of the system, the sum, density, and pressure. So this means that for any pressure you put in the system, this is why we still have one freedom, but it doesn't appear in these equations. So for any pressure, the evolution is the same. So if you have pressure, because we can give this evolution in terms of a modified, a combination of density and pressure. So then that's the reason behind that, the motivation behind that result. We started assuming this, so we didn't suppose that the energy conservation, the energy density conservation applies, and so we found that combination of equations here. So, okay, then we work out that the modified Friedman equation leads to this structure here. So this is somehow a radiation-like term plus a cosmological constant. There is no matter term here. This is quite different from lambda CDM. So for late time lambda CDM, this would be a 3, and then we understand what is going on here. So, but then, can we explain the observational data with that? So we are doing that right now, but because it sounds really strange, maybe we should go to strange things to understand the most natural ones. So what is going here? So this is the deceleration parameter in terms of this combination of 1 plus z, redshift. So as you know, lambda CDM, this is the matter phase, Q goes to 0.5, and then it transit to the accelerated region. So this is asymptotic future, z minus 1. Okay, this is the theta. Of course, lambda CDM, when we go back in time, we reach the radiation phase, and this black line goes to 1. So this scenario here is quite different. This is similar to that Hilbert gravity. So you showed in your poster, yeah. So the point is, it's matter, even if you put pressure equals to 0 to your fluid. So matter behaves like this way, like radiation, until, okay, recently, in terms of redshift, but this is billions and billions of years ago. And then from this radiation-like behavior, we transit as well to the de Sitter point in the asymptotic future. So the point is this transition okay with the cosmological data? Probably. Yeah, we are doing right now. And so Francisco I just discovered we started to do this investigation in parallel. That's why conferences are so nice. You see that people are working at the same time with the same things. So okay, so it sounds absurd, this model. No, it's old enough. It's at least old. It's not. So the age, if you calculate the age of the universe with this strange expansion here, it's okay. Because the age of the universe is, as I showed you at the beginning of the talk, depends really on this constant term here. This makes the universe older. So then if you put like omega u here, 0.9, you have a very old enough universe. Okay, then of course the typical question, but we don't have structure formation in this model because we don't have the matter phase as we think traditionally. No, but then we go to perturbations in this model, and they grow as a squared instead of a. They grow faster. So, of course, this is a completely different picture, absolutely non-standard one. We have a different expansion rate, and in principle, you don't have the matter phase, but structures go faster. They grow faster. And then the point is how to accommodate this and having a like of concordance unimodular cosmology here. Okay, this is what we are doing right now. I think I'm approaching the end of my talk. So, congratulations to the brave participants who were there yesterday. And so, muchas gracias, Chile. Thank you very much.
Okay, thank you very much for a very nice talk. I just wanted to point to you, or remind you, concerning your last subject of unimodular theory. You see, yeah, very good. So this is the point. This formulation of unimodular gravity fixes the determinant of the metric to a constant, which violates general coordinate invariance. As one of my first applications I show in my talk was that you can have something like unimodular gravity with the cosmological constant being a floating number, right? By using the alternative measures that are metric independent. So in that case, you still can have like a floating cosmological constant and unimodular gravity, right? Something like that. So apparently, if you restore the general coordinate invariance, you will not be able to have a non-conservative energy momentum tensor. I don't know, probably. That's just comment, yeah.
That's one, yeah. Very, very. That's only one of the possible and maybe, yeah, problematic versions of the unimodular setup, right? But
yeah, but you can restore the general coordinate invariance.
Aha.
With the use of non-Riemannian measures.
That omega, yeah. Yeah.
First of all, I enjoyed a lot this nice talk. I have maybe technical question that is related to the matter perturbation equation you showed. Is the effective Newton constant scale dependent here?
So the effective Newton constant will be, let's see, in G?
Yes.
And yes, G. Okay, no, sorry. No, it's not the effective G. It's like the friction term, which is scale dependent.
Okay, because in that case, did you consider the scale dependence of the initial condition when integrating your equations? Because usually people do not use them because in lambda CDM these are not important for F sigma 8, but in those kind of theory it is important.
Yeah, but so what we did here is to pick one scale, like still linear today, and so we take that number.
But even for this scale, the dependence, there is a dependence in the initial condition with the with the scale.
Yeah, the initial conditions depend on the scale.
Yes.
Yeah, for each scale you have different initial conditions.
Okay.
For sure. Yeah.
That was my question.
Yeah.
Okay, thank you.
But it depends on time.
Yes.
Yeah. So if you take the power spectrum at, let's say, at a redshift 3000, so yeah, you see that they depend on the scale. Yeah.
Any other question or comment?
Hi, thank you so much for your talk. I have a question about the constraints that you propose for any alternative theory. You say that you have like a 3 sigma contour limit on the tension. Maybe on the here. Okay, so this 3 sigma convention is only a convention or have a meaning? Like, why not 2 or 4 or 5? Like.
So people say that if you have a claim at 1 sigma, means that you are just starting in the field. You didn't understand how serious it is. So then you claim at 2 sigma. Okay, it's fine. So to really give a very claim with a very high confidence, statistical confidence, that you should go up the sigmas, of course. So I would say that 3 sigma is standard. The standard, I mean, 99.5% of confidence there. This is, I mean, the higher you go, of course, the better it is. But then you have more possibilities, right?
Okay.
But I mean, you can work climbing things at 2 sigma. Maybe it's not strong enough.
3D, I would say the 3D is standard.
I have a comment regarding this, because in particle physics,
exactly.
people use 5 sigma. This is, I think, what Matthias is asking. And I think there is a whole discussion to be done there about statistic and what criterion to take in cosmology, why should they be equal or not to particle physics. I think this is that is not established yet. No, it's still a question.
Yeah, it's more. Any other comment? Can I ask something about the last model? So is there a parameter value that goes back here in unimodular gravity to lambda CDM? So is there a limit in lambda CDM? Is the case?
No.
Exactly. So this is the important thing. Okay. Very good. Good. Because usually what people are doing is, as we say, reparameterization of our ignorance. So instead of having to explain the cosmological constant, you put one other parameter, and then you have always the lambda CDM limit in a different context. Yeah. Anyway, so any other comment?
Hermano, sí. Yes. Sorry, is there some equivalent, Hordenski equivalent theory or model for this theory, or just because, for example, we know some theories cannot be compatible with the, for example, the constraint for the speed of the propagation of the tensor modes. Yes, and then, for example, we know some sector of the Hordenski can be compatible, but not all. And then in this case, we can compatible with these constraints, or?
We didn't check the tensor modes here.
Okay.
Only the scalar ones.
Okay.
Yeah.
Was another comment?
Thank you for your talk. I wanted to ask you about what do you think about other methods to explain dark energy and dark matter, because maybe there are some authors that are trying to explain it using, for example, something related with the friction between photons and matter, for example. And also this effect can be maybe related with the rotational curve in galaxy, for example. Have you heard about that?
You mean interaction? Radiation? Photons?
Photons is matter, really. Yeah, it's something, I don't remember the physical concept. It's something related with the frictional behavior between matter and photons. Something similar to the gravitational redshift. Yes. Mm-hmm.
So you mean like these dissipative models, if you understood, like these viscous models? Because there is this type of model that, so maybe there is some at the beginning I told you, we assume that these fluids are perfect ones. So, but then maybe this kind of process, physical process, generates some dissipation in general. And yeah, there are models that wet this dissipation. So there is one specific physical process, which is the bulk viscosity, that it generates a negative pressure to the dynamics. The negative pressure, this means acceleration. So maybe it's an alternative that, so you don't have dark energy, you have only dark matter particles. And for some reason, and because of some dissipative process, on large scales, they have this effective negative pressure, and they could accelerate the universe. Yeah. This is a possibility.
Thank you. Anything else? So if not, let's thank Hermano again. Which one is this?
I send you to your mail the
Ah.
PPT.
You can send me?
Or now.
Or just? Yes.
In order to avoid the losing.
Maybe it's better the PDF. Or not.
Sí,
Preparar?
preparar. Ya, el PDF no importa. Solo al final tenía una animación.
PDF is better, right?
Yes.
Ver contenido, presentación.
Close this. Is it Control L?
Control L. It's not working. Ah, thank you. Thank you.
Okay, so let's proceed to the next speaker, which is Professor Desol Videla, and he is going to talk on cosmic slowdown of acceleration with the chaplets in Jacobi gas as a dark fluid.
Can you hear me back? Okay. Hello, everyone. Thanks to the organizer for giving me the opportunity to present this work, especially to my friend Giovanni, who has made a great effort to organize this meeting. Right? The idea behind this work is quite simple. You propose a modified equation of state of a matter that mimics the dark energy, and explore the cosmological evolution and possible consequence of deviation from lambda CDA model. This work is in collaboration with Jefferson Fortunato, Ippolito Ricaldi, who were William Ippolito is a professor at UFES University in Brazil. Jefferson is a PhD student, and José Ricardo Villanueva, a professor from Universidad de Valparaíso. I guess it's missing. It's not here. Okay. Here you have the archive coordinates of the works you are interested in. This is the outline of the talk. First, I would like to introduce the motivation. The motivation is obviously lambda CA model. Thanks to Hermano for giving a nice presentation and introduction about lambda CA model, which is basically the standard cosmological model that describes the evolution of the universe, starting from the radiation epoch up to the present era. Inflation, cosmic inflation, is a completely different state, which is considered as an extension of lambda CA model, right? This model is explained mostly, very well, mostly of the observations coming from supernovae, CMB data, and large-scale structure. Here you have the main matter content. Yeah? But in spite of the success of this model, this faces some theoretical and observational challenge. For instance, you have the cosmological constant and coincidence problem, which are basically theoretical issues of the model. And regarding observational issues or tensions, you have the tension between measurements of the Hubble rate, Hubble parameter today, and the sigma 8 tension and other more. But I think that this is more important. Probably we have new physics behind this model. And here you have these questions. Could the tensions between early and late universe measurements indicate the presence of new physics beyond lambda CM? Probably Emmanuel tomorrow will give us an answer to this question. Right? Here you have a non-extensive classification of dark energy model. First, you have the cosmological constant. Yes. This is the most simplest candidate to dark energy and explain the accelerated expansion of the universe observed today. Then you have the dynamical dark energy, in which the equation of state is a function of time. For instance, we have quintessence, K-essence, and phantom energy. And finally, modified gravities. Here you have some examples as F of R, modified parallel gravity, Brainward, and Hordetsky, and other more, right? Recently, we have good news for especially dynamical dark energy, because the first data from DESI, which is a dark energy spectroscopic instrument, if you combine this data with CMB and supernovae, it is possible significant deviation about 3 sigma, possibly for a cosmological constant in order to explain dark energy. The implication further exploration of dynamical dark energy in place of the cosmological constant in the lambda CDM, right? This is one of the most famous dynamical dark energy model, the Chaplygin gas. The Chaplygin gas is a theoretical fluid having an exotic equation of state, which is a polytropic one instead of a barotropic. Interesting, this kind of equation of state was studied initially in aerodynamics, right, from a Russian guy. And later on, was applied for the cosmological constant in order to explain dark energy. And this is a seminal work in study in cosmology, the Chaplygin gas. This is very interesting because at late times behaves like a cosmological constant, but at early time it behaves like a pressureless dark matter, which implies a unified description of dark energy and dark matter, right? However, this model has some issues, which are very important: instabilities and oscillations in the structure information. Yes, this kind of fluid modifies the growth of the structure, especially the growth rate. The rapid growth of the sound speed of perturbations, the fine-tuning problem, and incompatibility in some regions of the space of parameters with lambda CDM. But what about if we generalize the previous equation state, and here you have the generalized Chaplygin gas, we have a more flexible equation of state. Here you have a power of the energy density. You have the limit alpha equals 1. You recover the original Chaplygin gas, and in this case, intermediate case, this interpolates between dust and dark energy, and is more flexible in describing cosmic evolution. But again, you have these issues, the problems with structure formation, the rapid growth of the sound speed, CMB constraint and tension with observation, the Hubble tension and expansion rate, and other more, right? This is another modification of the Chaplygin gas, which is called the modified Chaplygin gas. You add an additional term, which is a barotropic term, which is linear with energy density. In this case, the exoparameter A allows for the model to have a more realistic and smooth transition between that matter and dark energy behavior. And again, you have basically the same problem with the other previous models, right? So what about with this family of Chaplygin gas and generalization and modification, right? So you have another modification to this equation of state, right? But we have a further generalization of the other previous equation, which is called Chaplygin-Jacobi gas. So let me explain how this kind of generalized equation of state can be obtained from inflation, right? Inflation, how do you study inflation? In the usual way, you start from a potential of the scalar field, and you solve the equation of motion, and you compute the inflationary observables and compare with CMB observation, right? There is another method which is called the Hamilton-Jacobi formalism, How does it work? Instead of start with a potential, you start with the Hubble rate as a function of the scalar field, and you obtain, for instance, the equation of state. Okay? You have this particular expression for the Hubble rate as a function of the scalar field. You recover the Chaplin equation of state in the case of a scalar field, right? So you have H naught and this capital phi, right? However, all we know that trigonometric and hyperbolic function are a special case of more general functions, which are the elliptic function. So in this work, it is possible to have a more generalized function, which is a Jacobi elliptic function. You follow the same procedure. You start, instead of the potential of the scalar field, you start with the Hubble rate as a function of the scalar field, compute the equation of, solve the equation of motion, and you have a modified equation of state instead of the previous one. So you have, which is basically generalized Chaplinian gas, a linear term with the energy density, and other extra term, right? So you have some constant k, is the modulus of the elliptic function, k prime k, which is a complementary modulus, and other, which are alpha and beta, alpha and b. You can recover, for instance, lambda CD model. If you set k to 1 and b positive. Another case, if you set k equal to 1 and b positive, and alpha within this range, you recover the generalized Chaplinian gas, right? So our starting point in this work is to have this equation of state for a perfect fluid, which is described dark energy. So in the cosmological context, we start with the Fermat equation for a universe which contains non-relativistic matter, radiation, and this kind of Chaplinian Jacobi gas. So you solve the continuity equation. You have the energy density for this fluid in terms of the scale factor. You put all together, right? And this is a dimensionless Hubble rate function for this model. So you see that it's characterized the space as parameter only for the Chaplinian gas. This generalized Chaplinian gas is three-dimensional. So you have alpha, Bs, which is a redefinition of B, which contains the energy density today of this fluid. So at the beginning, our space as parameter is three-dimensional, right? So in order to constrain the free parameters with observational data, we perform the Markov chain Monte Carlo analysis using three data sets. First by separate, and after a joint analysis. The first data set are the cross-synchronometer with this number of information of the Hubble rate compiled in this work. Obviously, time 1 supernovae using Pantheon plus the data set, which contains Cepheids and type 1 supernovae, right? And finally, FATS radio bursts, which had a great interest for constraint observational, using observational constraint in the recent years. So, the compilation is quite small, so there are only 23 data which contain cosmological information about the dispersion nature, which is related to energy, or the matter content, of the baryonic matter content. So, and finally, we perform the joint analysis. So you have here the results. Initially, the free parameters of this cosmological model are H naught, the matter content of today, and alpha, B, S, and K. But we set the the content of radiation, and the priors, which are usually used for H0 and for the dimensionless matter parameter today. So you have in this table the 1 sigma constraint for the separate analysis using cosmic chronometers, type 1a supernovae, fast ride bursts, and finally the joint analysis. So you can see that for the H0, the Hubble rate today, the Hubble tension is not solved, right? You can see Bs becomes negative, and the other parameter has half this value. The right hand side, you have the counterplot for the analysis up to 2 sigma level. So the idea is you have the results coming from the joint analysis from this parameter and see what happens with the cosmological evolution, right? And if that's possible to find some difference from lambda CDM. First, you have the relative deviation of the Hubble rate between generalized Chaplin-Gas model or Jacobi model and lambda CDM. So you can see that in the past, this is plot against C, you can see that there is no difference between this model. So just up to present epoch and the future, you have a significant, this is not significant, but it's some deviation from lambda CDM. So there is another way to study how a cosmological model deviates from lambda CDM, which is using the stage-funded parameter R and A. Now, you have the dimensionless Hubble rate, you compute some derivatives, and you obtain this set of parameters, and you compute in parametric way against C, and you can see that this point is lambda CDM, is fixed, it's a fixed point for lambda CDM. But obviously this model, as can you see, is you have some deviation from lambda CDM. In this plane, or S-plane, you have that the trajectory evolves at some point, which is basically implies a deviation from lambda CDM. A small deviation, but it's that deviation itself. Another important phenomena that is not observed in another kinds of Chaplin gas model is the cosmic slowing down. So you have here the deceleration parameter against C, and the the blue line is lambda CDM model, as this is a expect behavior, right? So at the future you expect the de Sitter expansion. However, for this Chaplin-Jacobi gas, the acceleration has a maximum at some value of 0.002, I guess, and in the future the universe starts to decelerate, as can you see, right? So you have this contour represents the 2 sigma confidence, right? So if you compare the evolution of the deceleration parameter between our model and the other kinds or families of Chaplin gas and modification and generalization, the other has the same behavior as lambda CDM, basically. So none of them is able to predict this kind of future that only predicts this generated Chaplin gas. So what happened here? Okay, we have used only 3 data sets. Okay, so you can see the values for the separate analysis are some different. So the joint analysis maybe works very well, but it is possible to include more data to have a more improved answer, right? So at background level, there is no difference between the evolution right? But what happens at a perturbative level, you compute the equation of motion for the density constant. In this case, it's different to lambda Cm, because in lambda Cm, the cosmological constant is not clustering. Right? But in this case, you have a component that evolves in time and is able to cluster. So this feature can affect the evolution of the growth of matter density. So here you have the coupled system of equation. So you have the coupling of this equation comes from the Poisson equation, thinking a Newtonian derivation of this equation, right? But in any case, if you start with the standard general relativity, it's possible to obtain the same.
It's delta dot since it's either, not there.
Oh yes, yes, thanks. This is a typo, yes, right? So you have a new evolution. So it's as possible that by solving this coupled system, the growth of matter perturbation is modified because you have another component that affects the dynamics of the system. So this is work in progress, and undergraduate student is working on this. So we expect that at the end of the year, I hope, we have the result. So in conclusions, we have explored, as a first approximation, generalization of the other family of Chaplin gas and modification and generalization. After the observational constraint, it is found that the universe has a maximum of deceleration at DC, and after it starts to decelerate. In difference between the other Chaplin gas families, this BS can be positive, negative. This is problematic because you can formulate on the other kinds of family of Chaplin gas the scalar field representation, and you can obtain the potential, right? In particular, for this kind of model, you can do it, the scalar field representation. You can compute the potential, but BS is related to the amplitude of the potential. So you have a negative value. So for that reason, the scalar field representation of this model, we are not interested in. So you have that, you see that there is no significant deviation in the past, but in the future, this model deviates from the standard de Sitter expansion. And the more important, which is the work in progress I showed recently, to distinguish between this cosmological model and lambda Cm is necessary to study the evolution of density fluctuation. This is a work in progress. We have no idea what about the findings. Okay. If Giovanni, let me. I would like to invite the master student and undergraduate student to apply to our PhD program, which is jointly with Universidad Santa Maria. The research lines are astrophysics, cosmology and gravitation, particles and fields, condensed matter, and complex systems. So you are invited to apply. The deadline is due the 15th of November. So you are in time yet to apply. If you are interested in applying or you are looking for more information, you can ask me. And thank you very much.
So, questions?
Very nice talk. I have two questions. First of all, you are not considering the Schuss data at all. So the 72, you get it from your model. Sorry? You are not considering the Schuss, the Cepheid Schuss data at all in your analysis. The data of Schuss, no. Not at all. So this 72 that you get for H0 is from your model, is a work, is a job done from your, for,
Is it possible to afford to work to consider this a...
no, but it's nice that you get this, because in Lambda CDM, you get only with the shoes data.
Yes,
Okay.
this is a first approximation.
Okay. And the other question is regarding the fast radio burst data. Why are you so interested in them? I see that they are not that constraining as the other data. Are there different redshifts? Maybe I missed something. Why is the interest in those data? They are not that, such, so constraining, this data. Why do you use them? The fast radio burst.
We honestly, some people think that they are not interested because you have a small quantity of 23. There are 24, but one of them is cosmological relevant. But just the first approximation. I mean, you have more data. You have more quantity of data, but it's just in order to explore, to study the implication for using this kind of data. But as you can see, the information about the observational constraint are so different. You can see the matter content is 0.25.
Oh, I see.
The standard. H naught is lower than the other.
Okay. And the last question, but just comment, have you considered adding the DESI data to your analysis? The BAO DESI recent data?
We have to consider.
I should. Yeah. You should. Thank you very much.
Another question?
Thank you, Nelson, for your talk. Yes, I have one question. How do you know the answer for the Hubble function at the beginning of your Villanueva model or your model? Thank you.
For instance, for the generalized Chapelin gas, you can do it at the contrary step. So you know that this is a question of time. So you compute this one. This is a generated function. So this is the answer. So you can do the process inversion.
Hi, Nelson. Nice talk. I have a single question regarding the value of Q at today, because the maximum acceleration is reached at redshift, you said 0.02, but today is still negative or is positive today? I don't see the...
This is the point of maximum.
Yes, but today it's
close to today. It's 0.
Because it changed
0.00.
so rapid. Okay, but it's still negative.
Yes.
Ah, okay.
Yes, it is negative.
So it's still not accelerated.
Just close in the future.
Yeah, in the future.
Anything else?
Hi, Nelson. Nice. So just a comment about the perturbations now. I think it's going to be, you said it's in progress, but it's going to be quite tricky because you have two deltas. Both of them behave as matter in the past, but now only one of them is like matter. And what is your feeling about, should you take both of them when comparing to the observations, only one of them? So, I mean, but when we start calculating the growth from high redshifts, so both of them, they behave like matter.
Yes, they have the extra pressure terms, which may affect the growth and the mass.
Yeah, I mean, but you should expect that both of them cluster, right? By the way, Chaplin is like matter in the past. So then you have these Chaplin structures in this scenario.
Our approach is, you have that energy, and this kind of Chaplin gas, this is not a unified structure.
Mm-hmm.
We consider this kind of Chaplin gas as some energy accelerate.
Uh-huh. Uh-huh. Okay.
Okay, thank you for your talk. This is a specific dynamical dark energy model, right? A specific dynamical dark energy model, right? The Chaplin gas to try to understand the Friedman equation is solved it. So, are you working with other models, in fact, like other kind of parameterization of the state equation? Yes, other model for dynamical dark energy model.
As I told you, there is a plenty of modification of this kind of the Chaplin equations. You can parameterize the equation of state, the CPL and other. We are focusing only on matter modification.
Okay. So, but you start there and you can parameterize in different ways.
It's not the unified description. You take the equation of state, you have the Chaplin gas, which is that energy that evolves in time. And additionally, you add matter radiation.
Okay. Thank you.
Can I also ask you something? So in the end that you saw the fits, your model here has two extra parameters comparing to lambda CDM. Yeah. But in the end, I mean, have you considered the information criteria like AIC or BIC or DIC in order to compare with lambda CDM? I mean, even if it behaves better, I mean, the chi-square is smaller, then you need to compare, the statistical efficiency of the...
Initially, we study the spaces parameter in order to have physical solutions. So in this first approach, the spaces parameter is reduced. So you have some relation between the parameters in order to have physical solutions. And then you perform the observational analysis and you find that the previous study is consistent.
Good, very good. Okay, so let's thank the speaker again.
Because I don't know Spanish, so. Is this mine? It's here. That's the board. It's not this one, right?
It's one of those, but it's asking me, it's not like able to. Let me plug it in, take it out and plug it in again.
answer here? Ah, no. Send it to Giovanni. I think he could send that through email.
Yes.
It's here. You have reminders. Hello. Puta. Restart. No, no, no. Remember to have also to attach them.
Yeah.
Is it a PDF or a
PDF. I have a lot of pictures.
Are you are
Do you have another pen drive? I cannot see. What is this?
No,
this is for the pointer.
Yes, for the pointer.
I'm gonna take out this pen drive.
Very slow.
Previously it was almost automatic.
This is iPhone. Maybe you can send by the cell phone.
Okay, now we're just
Okay.
2 seconds. Ah, you are using your data.
Yeah, because I'm not connected to, I don't know the password.
It's free. It's free.
Oh, okay. And I cannot connect directly to the laptop. This is finished.
Probably.
Still have.
Yeah.
iPad.
The mail needs also some seconds.
Yes.
Give you the chance
Yes,
to
from
answer.
the university also.
This pen that I connect to the university will be teaching computers, and I don't have any issue with the Windows.
Yeah. Okay.
No, it's okay.
Very good.
Bloqueado. Is it a virus?
No. It's saying that this
Okay.
just not gonna carry out the
Yeah, the test.
test, so it's
Okay.
at your own risk.
Yes.
But I,
Ah.
it's
Very
good.
good.
It's free of viruses.
Okay.
It's free of human viruses.
You see also if
40 seconds.
That's also slow.
yes, this is it's a big. It's full of figures, eh?
I have a lot of pictures and
Oh,
diagrams.
nice. Can you?
Okay, so the next speaker is Pedro Alvarez, and he's going to talk on cosmological model of uncongressional supersymmetry.
Thank you, and let me thank the organizers for organizing this nice congress. It's very nice to be here in the north. As some of you know, I was in Antofagasta until last year, and then I moved to the south in San Sebastián and Sex. yeah, I'm going to talk today about this cosmological model that can be constructed within the framework of what we call unconventional supersymmetry. Let me first, before I forget, to let you know that we have opened the PhD program in Universidad San Sebastián. We have these professors in our claustro, and we have also collaborators. We have a possibility of going to Santiago, Valdivia, Concepcion, and it's still time to apply. Okay, so the outline of the talk is the following. I'm going to briefly speak about the motivation, the why we do this. I'm going to show you how we do this. I'm going to talk a little bit about the kinematics that allow us to carry out this construction of models. And then I'm going to show some examples that are more relevant for us from the point of view of cosmology. I'm going to close with some future prospects. Okay, let me start with the most important point of supersymmetry, that is the fact that the Haglop-Sankisonius taught us is the only non-trivial mixing of symmetries that we have, space-time symmetries and internal symmetries. That's a theorem, a mathematical theorem, so that fact is not going to go away anytime soon. It's a very beautiful idea. It's a okay, and then the standard procedure is to construct models, as people did in the late 70s and 80s. So, for the point of view of particle physics, they construct a minimal supersymmetric extension of the standard model based on this recipe of Westbagger. For instance, you learn that by mixing the chiral supermultiplet and the vector supermultiplet, you construct a variety of models that are used in phenomenology. And this produces a very baroque, in our opinion, kind of models that contains a lot of free parameters. What's going on? And that means that in some sense implies a strong departure from unification ideas, which is a little bit surprising. You start with a bigger symmetry, and you expect to construct models that are somewhat inherit these unification ideas, but you get the opposite. You get more free parameters. And also is the fact that the superpartners haven't been found yet, and also there is no reconciliation with gravity theories from the point of view of MSSM models. And our proposal is that perhaps the supersymmetry is not being explored in the right representation. So let me thank my collaborators, especially Jorge Zanelli, Mauricio Valenzuela, that have collaborated in this topic, in this venue. Also some students from University of Antofagasta, Alejandro Chavez and Juan Ortiz. And so let me summarize the main idea. The main idea is to take a gauge connection of a superalgebra and include matter fields directly in the gauge connection with a, let's say, some little trick that I'm going to show you how it works. And as a result, we can construct models in which the matching of fermionic and bosonic degrees of freedom is not mandatory, so perhaps no superpartners are implied. Also, the theories or the models that we construct in this way are not completely crazy, so the kinetic terms are fairly standard. Also, models of this kind are going to be models that are highly predictive in the sense that we don't have 20 or 100 free parameters, since we are working with a unified gauge connection. All the gauge couplings are going to be implied, or there are going to be relations between the gauge couplings. And also, there are going to be, let's say, non-minimal couplings or new coupling with respect to the minimal coupling equivalent model that you could take advantage of to explore new physics. And so what's the idea? So we take a gauge connection. We have some bosonic fields and some fermionic fields. We have our generators, bosonic generators Gm, our fermionic generators Q, our superchargers. And some of these generators in a superconformal algebra, for instance, are going to be associated to space-time generators as the spin connection. There are going to be another kind of generators that are internal gauge bosons, your gauge bosons. You might have perhaps some bosonic associated to the central charges of a specific algebra. You're going to have extra new bosonic generators. And you're going to put your matter fields here with this trick that is using the soldering form or the tetrad in order to couple the indices appropriately. And so you're using this kind of field, which is a tensor product with spin 1 index and then spin 1/2 index. And this carries these two representations. So these two are reducible representations, 3/2 and 1/2. Normally in supergravity, you focus on this component. So you give an extra condition, which is the gamma traceless condition, to kill this component. And what we do, what we call unconventional supersymmetry, is to study this, let's say, orthogonal component of the Rarita-Schwinger field. This is automatically done by this composite field that is I was showing in the previous slide. This contraction. So it's a contraction of the field line, one Dirac gamma matrix, and your spin 1/2 field. That contraction is automatically killed by the projector to spin 3/2. And this is the one that we are going to be focusing on. Well, at least one of my main focus of research has been about this field. Okay, so this sounds good, but you still have to recover the standard gauge transformations. And let me tell you, this is no problem. I can't show so many details, but this you can see using standard differential geometry that you recover the standard gauge transformations for the bosons and for your matter fields that carry out the fundamental representation of your corresponding internal symmetry group. And at our disposal are this algebra series, the superconformal algebras in different flavors that you can find, like SU22N or SOSP P,4, depending on the dimensions and space-time dimensions and how many internal, how big is your internal symmetry group that you're going to incorporate. So it's not, what I'm trying to say, that it's not just a very specific example that works out for some exceptional group. It's for a whole series. Okay, so that's about the kinematics, and then what kind of model can we construct, or what kind of dynamics we can obtain from these models. In 4 dimensions, the possibility of constructing actions is based on the similarity with the standard simple supergravity models, which can be written in this way as the square of your field strength, where in between you put some operator that breaks down part of your symmetry. Yeah. So that kind of contraction is so that you obtain the standard Einstein-Hilbert term. Okay. We also want to obtain a standard Young-Mills component for your gauge bosons and the standard kinetic term for Dirac. And without going into so many details, I can say that in order to do so, you need to find some specific form of this generalized Hodge dual operator. That can be done. So that can be done, and it can be seen that, in fact, the ADS or the conformal algebra has embedded this nice structure, which is the fact that we have an embedded grading operator that separates the translation generators and GA, with the Lorentz generators, JAB, and that graduation, that grading of the algebra means that we can split the bosonic part of the gauge connection into an even part and odd part with respect to this grading operator. And that means that the Lorentz part of this symmetry is going to be like an unbroken, generally realized gauge symmetry, and the translation generators are going to be what people in supergravity call this broken symmetries or off-shell symmetries. So symmetries that, in order to be converted into local symmetries, require some extra subsidiary conditions. So that's why they're called on-shell. And this structure more or less gives you a unique candidate for how this dual operator acts along the fermionic part of your gauge connection. And that gives you, in the end, a standard Dirac kinetic term for your fermions. For the sake of time, I can't show so many details, but you can ask me more about this part. Okay, so in fact, in 4 dimensions, all of this structure with the dual operator is very beautiful. Like, you can take advantage of this structure. So basically, you take a standard differential geometry. You take this dual operator, this grading, you exploit this grading of the generators, and then you realize that implies that you have a grading in your algebra, and so some traces, these are super traces in your superalgebra, some super traces are non-trivial and have very well-defined parity properties, and some other ones are automatically killed by the supertrace. So that means that whatever kind of products we have in these cross terms are not going to appear in this action. Okay, so without this observation, you have to do all the computations by hand, and it's a very tedious calculation. But with this observation, everything comes out very clean and easy to understand. And so that means, this property means that the fields are along these components. So all the generators here that include translations in the superconformal algebra are going to be auxiliary fields. They're not going to have their own kinetic terms. So those fields are not going to be dynamical in these theories. So which is a welcome feature, because they are new fields with respect to what you have in Einstein-Hilbert. Those fields are the fields that go along with the translations, so ADS translations, or superconformal, special conformal generators. And so those fields do not acquire independent kinetic terms. In fact, those fields have cubic and linear terms, and that means that we are also in a different kind of theories in comparison to conformal supergravities. And more nice properties of this dual operator is the fact that under general variations of the action, we can write this very simple formula in one line instead of doing this huge computation that you have to do with term by term in terms of the field strength component. And so the field equations can be written in a la Young-Mills, but with the only care, with the only subtlety that this covariant derivative acts on this generalized dual of the even parts of the connection. And that means that we can easily take an integrability condition by taking an extra exterior derivative, and we arrive to this condition. This condition encapsulates all the integrability conditions that you get in simple supergravity, which here I'm not writing, but it corresponds to length expressions of the field strength components. In terms of this operator can be computed in this way. And some parts are identities, which is when you consider a group structure like for Young-Mills, when you don't have all the symmetries are genuine gauge symmetries. And then we have new components that, for instance, this one is a fermionic part of your field strength with the dual of the fermionic part. This on the right-hand side, because of supersymmetry, you have bosonic component, and those bosonic components are on-shell conditions. So the usual on-shell conditions that you get on simple supergravity. And then you also have conditions, and this kind of components of this term implies conditions on the fermionic components. There are also on-shell conditions on supersymmetry. Okay, good. I think that I need to hurry up because of the sake of time. And so in the study of the bosonic sector, of the gravity bosonic sector, this theory is now is a bigger theory than Einstein-Hilbert, but it contains Einstein-Hilbert in one specific sector of the theory. You know that by looking at the bosonic component of the field equations. And if we focus on a purely bosonic sector in which we set all the spin components to 0, we get these are the components of the field strength. This is the bosonic action. Here you can find the ADS gravity action that contains Einstein-Hilbert plus cosmological constant plus Gauss-Bonnet. These are your field equations, and then you realize that one sector of the theory is can be found in this by this ansatz. So your dual fields to translations and special conformal transformations are proportional, let's say, to the field line. They carry the same index structure from the point of view of Lorentz transformations. So, and then you you check the consistency of the equations, and that's a good sector. And you can find a whole set of solutions that are asymptotically ADS, asymptotically locally ADS, with this kind of answer that we studied with Cristobal Corral during the last years. But from the point of view of cosmology, is in fact the simplest case that is more relevant, in which this proportionality constant, the proportionality fields are constants, and then we recover cosmological constant. We recover the cosmological constant term in the action. Okay, so that would be what we call the ADS background of these models. That's a sector of this theory. But then these are very restrictive conditions, so a more general background would let these proportionality coefficients to be fields, or to promote them to fields. So it's just, you can look at it just as scalar field. Okay, let me now go on into cosmology. Basically, cosmology rests on top of these three big pillars: dark matter, dark energy, and inflation. Three of them are their own mysteries on their own. The typical simple model that we use to understand cosmology is lambda CDM that is basically general relativity, including the known content of particle physics. It also includes cold dark matter. We add some cosmological constant term to describe dark energy, and we also add inflation to describe the adiabatic initial conditions. And then we contrast the predictions of this model with a series of observations. We have big classes of them, like some observations come from BBN, Big Bang nucleosynthesis, some other ones from properties, studying properties of the CMB. And there are also some observations based on late time universe, like supernovae precession, and also the formation of large scale structure. And then we take our model, or favorite model, or lambda CDM, and we compare with these observations and to obtain the best values of our parameters of our model. That's in a nutshell what we do in cosmology. Whoops. And what's been going on in the last years, in the last decades, is that with the improvement in precision of the measurements, it started to become apparent a tension between different kind of measurements, the ones based on early universe or CMB properties, and then observations based on the on the distance ladder, on the supernovae and Cepheids and cosmic chronometers. And now the error bars are too small. So now we, as Matthias explained us in his talk, they started to become incompatible now because this precision is just too good. Okay, so one specific thing that we can look into cosmology is to look at at a characteristic separation between galaxies that is imprinted or inherited from the CMB, from the separation of the peaks in the CMB. Okay, and that is largely dependent on the sound horizon at the coupling. And if you look at the RS H0 plane, you can see these contours. Very elongated from this point of view, but it's a contour. And then you can suspect that by reducing the sound horizon, you might find a region in which they are indeed compatible. And so from the point of view of lambda CDM, you cannot solve this tension, but some people started to, a lot of people started to propose ideas to solve this tension that are based on new physics. So not just a modification of the contents of neutrinos, but completely new sectors of the gravity theory. So in particular set of theories are these scalar tensor theories that include one or more scalar fields, and they can replace completely or partially the cosmological constant terms. So they model they provide you a model for the dark energy. Among them, there is this particular model which is induced gravity that, to our surprise, we can find naturally embedded in these unconventional supersymmetric models. Okay, so you do the computations, then you study the most general sector of when rho and sigma are fields, and then you arrive to this model, induced gravity. So this induced gravity model is a particular case of scalar tensor in which you have no minimal coupling to the Ricci, and you also have potential. And the kinetic term is canonical. And the potential is a power of the non-minimal coupling. Okay, in this case, we have two parameters at the level of the action. Okay. And so this, as I was saying, is a particular case of scalar tensor theories in which you have a potential and an independent function for the non-minimal coupling. In these cases, in general, you obtain your two generalized Friedman equations and this equation for the scalar. So that's your dynamic. In the generalized Friedman equations, you can see that now what multiplies the Hubble parameter square is this function f. So now you don't have any longer Newton constant. The equivalent of your Newton constant is a function that could evolve in time. And so these theories are still very pretty because the conservation laws are still valid. It's still a metric theory, so if you apply covariant derivative, you still obtain conservation laws, but they are just modified with respect to general relativity. So you can construct effective density and pressure. Let me give some brief comments about the physics of these models. You also have, from the point of view of cosmology, then you can see in these equations that I can write them this way, and then I divide it by this function on the right-hand side. And then I have, from the cosmological perspective, I have this effective Newton constant. We have Copper-Venturi provided this very simple approximate solution for when we have one component of perfect fluid. And from this solution, you can see that when the parameter of state takes the value of 1/3, then your Newton constant is exactly a constant. But as long as you deviate from this value, the Newton constant is going to start evolving. So for values of these parameters, typically what we call the W smaller than 1/3, this Newton constant is going to decrease or increase for values bigger than 1/3. Okay, let me just so we've been studying this model recently. This is the autonomous system in order and in general, if you have more than one component, then you don't have analytical solution, so you have to study the autonomous system. The regime of your parameters are going to be the parameters in the action, also a couple of parameters associated to your contents, and also new parameters associated to your initial conditions. Okay, so those are your parameters of your new cosmological model. And the typical physics that works with observations is that deep in the radiation area, the scalar field is nearly frozen. Then in the matter-dominated area, this field is dragged by the matter component to a larger values. It mimics the tracker behavior of quintessence models, thanks to the non-minimal coupling to the Ricci. And then at late times, the potential kicks in and the model behaves like dark energy. The field remains frozen at certain value, and then the model starts behaving like dark energy. And for some very important point is that the mass term, the effective mass term of this scalar field has, for this kind of induced gravity models, is exactly 0. But this physics works the same way for as long as that effective mass term is very small. So it doesn't need to be exactly 0. Okay, good. Let me just move on to what we're doing recently with respect to this model. Since we have also for Cavendish-like experiments, you also have an effective Newton constant that is different from the one that you observe from cosmology. And so there are also constraints that come from that point of view. Okay, I'm going to skip some of these details. And so many authors have explored these models to ease up the tension in H naught. The final result is that you cannot solve the tension entirely, but you can ease up the tension. But on the other hand, you can also obtain constraints for the non-minimal coupling. And from using cosmological data, you can obtain very good constraints. So this parameter has to be smaller than 10 to the minus 4. And one observation is that the absolute luminosity depends on the value of G. So in theories in which G evolves, this can produce constraints on your model. And so with the improved data set of Pantheon plus Shoes, we are exploring the confidence intervals and hoping that this term is going to improve the constraints. And these are preliminary results. Here I have some marginalization of parameters. Here we have H, and this is log 10 of gamma, the non-minimal coupling to the Ricci. And these are contours in blue. Here I overlay the contours of Shoes. And in colors, we have the predicted value for the G effective for Cavendish-like experiments. And those experiments provide you an independent way of constraining G. And so you can see that only part of the, a big part of your confidence region is in red, which are values higher than permit, are in the forbidden region of Cavendish-like experiments. So this slice of the hyperplane of parameters is very nice because we can constrain this confidence interval. We also exploring other slices. You can see that in this case we have in the vertical axis the initial value that you set up this scalar field deep in the radiation area. That the value is normally fixed to 1 for the sake of naturality arguments. But in reality, there is a range that is fine with observations. So you can see a scatter of blue, red, and green dots here all over the place. So that means that the Cavendish-like experiments would not provide, wouldn't tell you anything about the actual initial value of this field. And a similar thing happens in the slice of omega matter H of the hyperplane. And finally, another thing that we've been exploring is the. Okay, good. I'm going to close with this. It's just exploring the effects on the state finder parameters. We have the deceleration and the state finder pair proposed by Sani, Seine, Starobinsky, and other people that are functions that are defined in terms of derivatives of dimensionless functions, defined in terms of derivatives of your scale factors, so in some sense geometrical, and help you to characterize or compare different models. Here, lambda CDM lies on the R equal 1, and for instance, for quintessence, you have a vertical line that goes in this plane, in the RS plane, in this way. And so now, recently, some people have been using observation to provide constraints on this the deceleration and the jerk parameter, which is also related to, is another definition of the third derivative. And so we've been also using the data of Pantheon to look at the constraints on our induced gravity model. And with that, I finished. And there are other things that can be done. And we are building up the knowledge in order to include more terms that are implied by unconventional supersymmetry. And hoping that perhaps those terms that are implied by the non-minimal coupling can also have influence in the cosmology. There are a lot of things that to be done in this line. Thank you.
Thank you very much. So, questions or comments?
Thank you for a very nice talk. In your model that you presented with the sigma field, right? You don't have any possible master there, right? Because it's perfectly scale invariant, right? And but I think, for example, in the model that Z presented, he called it also induced gravity. He has an inverse mass term, so this gives you spontaneous symmetry breaking, right? And it's like more because somehow the scale symmetry you have to break it, otherwise you get into a lot of trouble.
Yeah.
You have the possibility to introduce this inverse mass term so that you can break spontaneously the symmetry.
Yeah, I think we do, because now as a starting point we are studying just the bosonic sector of the theory that's appropriate for cosmology. So we still have, so we turn off at this stage the fermion, which could be interpreted as a dark matter candidate, let's say. That's, in the meantime, for us, completely off. But that's a whole new story that we have to include in these models. So this is just the beginning, let's say.
Yeah, because the Z model has been studied in inflation and stuff. That gives very good results.
Okay, I will look into it. Thanks.
Yeah.
Any other comment? I have a question. So concerning the values now, the quantitative analysis. So you have a supergravity model, I mean, modified in the beginning, and you have some energy scales, some masses. So you have some things that determine you the scales. So in the end of the day, of course, you obtain an effective cosmological constant and the whole cosmology. However, quantitatively, the values that you expect the supersymmetry to appear are in agreement. So in the end of the day, you're obtaining a cosmological constant with the exact value that we're measuring. I mean, 10 to the minus 36 electron volts, or is there a freedom there to play?
We don't measure the cosmological constant. So when you compare to the prediction from your favorite model, like lambda CDM, you have to be careful. And so sometimes it's convenient to define effective quantities that follow the same continuity equation as you would use to infer values from a lambda CDM model, assuming that your underlying model is a lambda CDM. So when you compare things, you need to be careful. So let's say, for instance, I have a inferred lambda here. It doesn't compare one-to-one to the lambda that I would read from a lambda CDM model. So I have to look at the contours from an agnostic point of view, and then obtain conclusions. And also I have to go into the observables and so.
Thank you. Any other question? If not, let's thank the speaker again. And now let's have a coffee break.
Very good model. What I asked before is that initially you start with the model. So, and you have some masses of
particles. There is an information. So you have some parameters, and you expect, for instance, we know the level that supersymmetry should appear. I don't know if this is TV or whatever, but you start with something. So in the end, you do all this reduction, and in the end of the day, you obtain the effective Friedman equations. And I would expect that your initial parameters to be there in the end, right? This is what you said, the sigma, all these fields, and the masses, the lambda, all these parameters. So, in the end of the day, you obtain an effective cosmological constant depending on this small lambda, sigma, what euro, psi, all this kind of stuff. So the value is just quantitative that you obtain. So if you start with a supersymmetry energy scale of 10 TeV, in the end of the day, the cosmological constant will be small, or this is what I'm trying to say.
So one thing is that the naivest background of this theory that connects with gravity implies a cosmological constant of the order of the Planck.
This is what I'm asking.
Yes.
Exactly.
Yes, that's always a problem. So when you construct these models with this probably very, very slow. You construct these models in the naivest way, you don't have any free parameter, and then you have this issue that is typical of
yes, I know.
So we say, okay, the recipe has to include a dimensionless coefficient in front of the action. Good. Because we can define this generalized dual operator, but we are not able to say anything about a global coefficient in the action. That could,
yes.
And with that one, you can then accommodate small cosmological constant. And that's all. That would be lambda CDM because it's just constant. But then, in reality, the background of the theory is a field.
No, yes.
So it's natural.
Good. Very good.
Yeah, thank you.
Sí, lo que pasa es que hay cuatro contribuciones a la medida de dispersión. Sí. Y hay modelos de los progenitores, entonces en verdad es muy distinta. Claro. Por ejemplo, está la densidad de variones, y la dispersión puede calcular cuánta materia perdida. Bueno,
Professor? ¿Puede me escuchar? Francisco? Creo que no me puede escuchar.
Sí, está saliendo. Sí, está llegando el audio.
Ah, ya. Ah, ahora está funcionando. Francisco? ¿Puede me escuchar?
Olá.
Oi, Francisco.
Olá, Giovanni.
Como estás? Ah, muito bem, você?
Também, obrigado.
Muito obrigado. Sim, tudo bem. As coisas estão indo muito bem aqui. E estou muito feliz que você esteja vai fazer o seminário para nós. É muito importante para nós que você possa fazer esse seminário, não?
Muito obrigado, Giovanni. Também, olha, obrigado também pelo convite, está bem? Que muito me honra também. Eu gostava de estar aí pessoalmente, mas é muito longe.
Tá. No, obrigado você. Aqui está Emanuel Saridakis, tá? Eu sei que vocês são colegas também. Sim. Também está não sei se você conhece do Brasil, o irmão Belten.
Ah, conheço muito bem.
Sim.
Eu estive com ele, tive com o irmão na Rússia, em Kazan em 2018, salvo erro. Nós estivemos lá. Também teve lá o Júlio...
Fabrício, sim.
Fabrício, exatamente. Sim.
Muito bem. Sim, o irmão Belten falou mais cedo, não? Comentou alguns papers de você, não?
Sim, foi?
Sim.
Muito bem. Então diz-lhe muito obrigado.
Tá. Ele vai estar agora aqui, né? Tá bem?
Ok. Olha, tu agora estás aí em Arica, não é?
Em Arica, sim.
Onde é que fica Arica?
Arica fica no borde na fronteira com Peru. É a cidade mais no norte do Chile.
Ok.
Sim. Ficamos na fronteira com Peru, Bolívia e Argentina também.
Sim. Ok. Muito bem.
Tá. Você bem-vindo. Eu gostaria que você visse na próxima vez, tá bom? Para que você conheça aqui. Tem muito lugar legal para conhecer. Tem o Museu das Múmias mais antiga do mundo, o Morro do Arica.
Sim.
O pessoal está desfrutando muito. O Emanuel está desfrutando muito. Todos estão desfrutando muito, hein?
Ok. Sim, o Emanuel conhece muito bem o Chile, não é? Ele... Sabes que a primeira vez que eu conheci o Manos foi no Chile, foi há 10 anos, foi em Valparaíso.
Tá.
Também estavas lá na altura, foi num encontro que houve lá na Católica, não é? Do Valparaíso, que foi organizada pelo pessoal de lá, não é? Agora esqueçam os nomes das pessoas, não sei o nome dele, o Joel Salvaedro, não é?
Tá.
As pessoas, não sei o nome delas, não é? Mas
Joel Saavedra.
Não estavas lá em 2014.
Tá. Tá bem. Legal, hein? Muito legal, hein?
Tá bem. Muito bem, sim, senhor. Olha, está um bocado atrasado, não é? O timetable está um bocado atrasado, não?
Desculpe, não estou entendendo.
O horário das palestras estão um bocado atrasados.
Um pouquinho, sim.
Está bem.
Sim. Okay. Talvez uns 15 minutinhos, 10 minutinhos, mais ou menos.
Sim. Giovanni, posso fazer um teste muito rapidamente, se eu consigo partilhar? Sim?
Sim, por favor.
Então,
vamos tentar aqui.
Ok. Tu consegues ver, não é? Consegues ver, sim?
Ainda não. Você pode habilitar a câmera também para a gente poder ver você? Se
não
você
está.
puder.
Deixa-me só ver então, peraí. A câmera está, a minha câmera está ativada.
Tá. Aqui no computador posso ver você, mas na tela principal ainda não.
Não?
Já entendi que que a pessoa técnica está abrindo o Zoom no computador principal.
Sim.
Agora sim. Agora sim posso ver você.
Estás a ver, não é? Sim.
Sim.
Tu vês os slides?
Sim, posso ver.
Sim?
Posso ver e posso ver você também.
Muito bem. Ok, está bem. Ok, então eu vou interromper a partilha. Está bem, está tudo bem então. Muito bem.
Tá bem. Tá tudo certo. Você está indo depois de dois short talks de 15 minutos. Agora o pessoal está no coffee break, então vou chamar eles para eles vir para aqui e depois dessas duas pessoas vai você.
Ok. Está bem. Muito obrigado, Giovanni.
Eu enviei para você a programação, certo?
Não tenho. Deixa-me só ver. Eu acho que não tenho porque não está online.
Está no
online,
site.
No link da conferência e
Tá.
posso ver os nomes.
Tá. Mas posso enviar agora para você no e-mail, pode ser?
Sim. Muito obrigado.
Eu vou enviar para você.
Giovanni, no link da conferência nós podemos ver os nomes das pessoas, mas não se vê o título das suas talks.
Os slides, like this?
Não. No link, no site da conferência, não se consegue ver os títulos, das...
Sim, entendi. A gente não colocou os títulos, mas sim, a gente fez impresso aqui para eles, colocou a gente entregou para eles a programação com os títulos, os resumos. Eles têm aqui presencialmente, mas não no site. Foi uma pena, um erro da gente, sim.
Ok.
Mas agora eu vou compartilhar com você a programação para você ficar sabendo, que você vai após duas pessoas.
Tá bem.
Mas eu acho que depois a gente pode atualizar o site e colocar os slides também, para que as pessoas possam acessar depois do congresso também.
Tá bem, ok.
Seria bom, né?
Seria bom ter os slides, não é?
Sim. Agora, a gente sim está transmitindo, vai
Juan Cabello. Ya.
Está ya.
Listo.
¿Esto es mío?
Sí, puedes tomar, sí. Sí, está. Now it's ready.
Ya. Ahí está.
Sí.
Yes. Okay, let's take our seats. Now, the party is over. Giovanni, what is this room? Okay, so let us continue. The next speaker is Juan Cabello, and he is going to talk on consequences of non-Gaussianities on the advantage of primordial black holes.
Thank you, Emmanuel. Thank you to the organization committee for inviting me, and of course, thank you all for coming. So, I'm Juan Cabello. I'm a master's student at Universidad de Chile. I'm going to talk a little bit about what I've done in my master. So I'm going to talk a little bit of what I've done in my master's. My presentation will be split into two main topics. First, I'm going to talk about primordial black holes, and then I will talk about the primordial statistics. With primordial statistics, I mean the statistics of the primordial curvature perturbation. So let's start. First, what are primordial black holes? They are hypothetical black holes that could have formed in the early universe that was dominated by radiation. There are several formation mechanisms. I'm going to focus on a particular one. That's the collapse of large-scale density perturbation that come from inflation. The theoretical bounds are pretty big. From the lower bound, that's the Planck mass, and here the upper bound is, 10 to the 6 solar masses, like a supermassive black hole. So they may have a pretty big theoretical mass range, but they are also severely constrained by different experimental, observational, and theoretical bounds. And in this plot over here, every contour, every area that is colored is a forbidden area. So for example, here in the left, the evaporation stands for the Hawking radiation, and it means that black holes that are lighter than approximately 10 to 15 grams would have already evaporated today, and so they cannot be observed. My motivation is threefold. First, they are an attractive candidate for dark matter because we don't need new physics to create new physics to explain them, but we need new physics to form them. So the formation mechanism goes beyond the standard model. Secondly, they may be the seeds of the large-scale structure of the universe and also the seeds of the supermassive black holes. Finally, with them, se pegó. Thank you. No. ¿El control? ¿Estará la pila como...? Bueno, igual puedo... Ya. So I was saying, my final motivation is related to inflation, so we can prove inflation at a smaller scales than we currently can see. What we are allowed now is this red line over here. That's the given by the temperature map from Planck. And the scales accessible by PVH could be from here, and I'm going to actually talk about even smaller scales. Vale. So some interesting mass windows are the following. PVH, their asteroid mass may constitute 100% of dark matter. Stellar mass PVH may explain the signals detected by the LIGO-Virgo-Cagra collaboration, and Earth mass PVH can explain some events detected by the optical gravitational lensing experiment, some microlensing events. This is the mass distribution, so the mass window that I just told you about are presented by those black curves. The PVH abundance, the main observable that is for my interest, is this beta. That's the ratio of the energy density of PVH over the total universe energy density at formation time. And if we have a PDF telling us the distribution of the perturbations, we can then obtain the abundance by integrating the PDF over some threshold. Omega PVH is the total abundance of the PVH the total PVH abundance that we obtain by integrating the previous quantity and considering a evolution factor. Finally, the delta L is the smoothed density perturbation that is related to the invariant quantity, the curly R, the comoving curvature perturbation. Well, the mass function is the curve that we saw earlier. If we integrate it, we can have the total fraction of dark matter that is composed by PVH. Yeah. This slide over here is very important. So we have in blue some density perturbation that comes from inflation. In red, we have the Hubble horizon. First, we need that the perturbation are higher in amplitude than a threshold, and those can collapse into black holes. If we have smaller than those, they will dissipate into a background. The circle, as I just told you, is the Hubble horizon. So when time increases, the size of the Hubble horizon also increases. If the Hubble radius is of similar length than the wavelength of the amplitude, then it will create a black hole. When the Hubble radius increases even more, then some bigger perturbation will re-enter the universe, the Hubble horizon, and then we'll have a bigger PVH. As attractive as they may be, we have also difficulties in them. In particular, Their formation requirements are quite strict. Here is the power spectrum of the CMB. We know this by Planck. These are currently the scales that we can prove, and single field inflation, well, describes quite nicely their dynamics. We need that this amplitude is at least 7 orders of magnitude higher. Also, a question is, well, we know that at CMB scales, this works well, but the question is, can we affirm that the almost scale invariant power law is the same at all scale? So that's what I tried to say here. I would say that no, it's more natural to think that there are more than one scalar field in the early universe. If they interact in a non-trivial way, then we will have non-Gaussianities, and that will leave imprints of the power spectrum. In particular, the model that I used is a rapid turn multi-field inflation that gives this power spectrum. We have the required enhancement, and at larger scales, or CMB scale at least, we recover the amplitude of the CMB. The most important parameter is delta theta. That's the total angle swept. So if we have two fields in multi-field inflation, they will interact with a turn in parameter space. The total angle that they describe is delta theta. If delta theta is around 4 pi, then we have the enhancement that we want. Lambda 0 and delta n, that is a linear combination of them is the angle. The lambda 0 parameterizes the sharpening of the turn, delta n the duration. The first thing that I did in my investigation was to study the parameter space. Here I have the same power spectrum, but with different sharpnesses. And the second thing I did was, I have a power spectrum. It has a nice structure, but I need to see if it is a low observational. So this again is a constraint parameter. Here I have my power spectrum, and an interesting part is that with the model that I chose, this power spectrum or this model may be tested in the future by LISA. Next, I'm going to talk about the primordial statistics. So the quantity that I'm interested in is the primordial curvature perturbation. If we have a adiabatic initial condition, every perturbation can be described by a single perturbation. I consider it in zeta, or the curly R that I told you at the beginning. When I obtain the abundance of PVH, I will integrate this tail beyond this tail of the perturbation, so a tiny deviation of the Gaussian behavior will result in different abundances. For example, I have here a non-Gaussian PDF, and for example, this model tells me that at this scale, I have a preferred scale. So at those scale, for example, I will have some more abundance of PVH. Next, how do we differentiate between Gaussian and non-Gaussian statistics? We do it by the Wick theorem that tells us that every higher order endpoint function can be described by the power spectrum, the two-point function. So if we know the power spectrum, we are done. We know the whole statistic of my quantity. I'm going to consider the first non-Gaussianity, the leading order. That's the Fourier transform of the three-point function, the bias spectrum. And it enters into action as this term, where psi is the isocurvature or entropic perturbation. That's the second perturbation. The first one was curly R, the curvature perturbation. I plotted the bias spectrum. It's a function of 3 parameters. Well, K1, K2, and theta. Theta is the angle between these momenta. And I found that they peak at equilateral configuration. So that means that when K1, K2, and K3 are approximately equal, I have my maximum in signal. I do perturbation theory around a Gaussian distribution, adding a small non-Gaussianity that is parameterized by this B function, and it depends on the bias spectrum. So my results. My non-Gaussian PDF, maybe one of my most important results is this one. Zeta 3 is the smoothed 3-point function. It depends on the primordial bias spectrum, and these same functions are some quantities that smooth the perturbation. They are a filter saying, well, I want to consider perturbation of this size to form PVH of this size. I plotted it. I have two parameters, two window functions. They have different behaviors. So the mass function, the quantity that we plot and we use to impose constraints over, is this one over here. In this inset, you can see that when I consider the non-Gaussian case, it slightly decreases. For example, the purple and orange curves tells me that I have almost 100% of dark matter as PVH. When I consider the non-Gaussianity, it decreases 30%. Yes, monochromatic black holes is one. I consider that every black hole is composed of the same mass. On the other hand, I have this extended mass function that the relation between the mass of the PVH is slightly more complicated. MH is the mass of the horizon, and well, the mass function is extended, so from there comes the name. The behavior is similar in both cases. Next, I plot here my two mass function. I see that they are in this window, that they are not restricted by the observational constraints. And in particular, in this mass range, PVH may compose the entirety of dark matter. I have here my summary of results. It's not necessary to describe or the whole table, just follow me with the first line. So FPVH, the fraction of dark matter as PVH. In the Gaussian case, I have 100%. If I use the positive non-Gaussianity, it reduces almost 30%. If I consider it in negative non-Gaussianity, the fraction increases by 40%. These are just numbers, and well, I know that I can't have 300% of dark matter as PVH. That's not physically possible. The final three columns are the same, but for the extended case. My main conclusions are that the oscillatory behavior that was describing the power spectrum and bias spectrum is not inherited by neither the abundance nor the mass function. Just as I told you, considering a positive non-Gaussianity reduces the total fraction of dark matter as PVH, while a negative coupling increases it. And, well, the bias spectrum peaks at equilateral configuration. So, is there a way to relate our parameters with the FNL parameter that appears when we consider a local non-Gaussianity? That's an open question, and I want to follow up my work with that in that line. Also, for future work, I'm considering constraining the parameter space, in particular lambda 0 and delta n, and then, well, what insights can I draw from inflation? That's a very interesting question in my opinion. Also, I may extend my work to consider other mass windows, like the other two that I showed you in the beginning. And some refinements to my work would be improve the numerical part. My code is expensive. It uses too much resources. It's slow. I can also refine the theoretical part, considering a more physical PVH formation mechanism. And finally, I could also use my PDF to compute other PVH observable, like PVH clustering, merger bands, etc. That was all. Thank you very much.
Very good, thank you very much. So, questions? Okay, I have two questions. The first is the following, very nice idea. However, you didn't consider a specific model to generate this initial PBH spectrum, right? I mean, you can have a freedom there, right? So this is the first thing, and most important question is the following. So in the end of the day, because we are expecting that to see, for instance, in LISA, through gravitational waves. So you need to do the final thing how this non-Gaussianities in the PBH structure will transform to the non-Gaussianities in the gravitational wave, in the stochastic gravitational wave spectrum, to measure that, right? Yes. I mean, have you considered this step, or have you done something?
Yes, actually, well, first, how does LISA detect PBH? PBH are formed in very small scales, which lead to very big gradients, and that form ripples in a space-time that are going to be detected as gravitational waves. Secondly, the stochastic wave background of gravitational waves was studied by my advisor, Gonzalo Palma, and well, a group from Paris also. There's a work already written in that. I can show you the reference later. And yes, the thing is they obtain some parameters, and it's also model dependent. Like I fine-tune my model so I can see what I want to see. So yes, and the first question I forgot.
Whether you have considered specific inflationary models to give you specific distributions.
Yeah, so for example,
for instance, you want to have an inflection point or something in the potential.
The model that I'm using is, well, this one. Yeah. I have two, this is the parameter space. I have two arbitrary fields. They interact with each other as a turn. That's the delta theta parameter that I was talking about. And well, yeah, this is the like a geodesic. In single field inflation is what we see like the slow rod potential. Here I have a very abrupt, sharp interaction, and then I recover the geodesic. This part over here, we can consider that the inflaton is the perturbation in the parallel line of the velocity. And the entropic or isocurvature perturbation is the direction of the velocity that is perpendicular to the direction of inflation. Yeah. So when I'm turning, those velocities interact with each other, and in particular, the isocurvature perturbation sources increases the curvature perturbation.
Good. Any other question?
Thanks for your talk. I have a naive question. I would say that it is under study yet the post-inflationary evolution of inflationary observables, for instance, power spectrum and higher order statistics. What happens with the Weig spectrum after inflation? Have you considered a post-inflationary evolution, for instance, during reheating phase?
That's a very good question. In our model, we find analytical closed expression, and for that, we need that this interaction, this one over here, we consider it as it's turn off, it's turn on, it's turn off, right? So it's a top hat profile. For the Weig spectrum, we assume that the perturbative coupling acts the same. So it is only on when we want that it is on, and that's during inflation. We have not considered any of reheating. I think that would be a really good investigation line, but it's currently out of the scope of our work.
Mm-hmm. Thank you. Oh, very nice talk. Does it bother you that this Lagrangian violates all the symmetries, Lorentz symmetry, whatever?
you violate all the Lorentz symmetry, right? Or it's not Lorentz invariant. And there is serious constraints on Lorentz invariance or something.
Can you repeat? Sorry.
This Lagrangian, say you consider it in flat space, it just violates all the Lorentz symmetry or something. For example, you have a term that has a temporal derivative, and it doesn't appear a similar term in spatial derivative. So all this violates Lorentz invariance.
I don't know actually if they are valid in Lorentz invariance, but I do know that this Lagrangian violates the canonical commutation relations during the time that the interaction is turned on.
Yeah, but apparently it violates Lorentz invariance. But okay, something to look at.
Yeah, thank you.
So I think we should proceed. So let's thank the speaker again.
Change the transparencies.
You cannot fit
What
it
is
to
it? Says,
This is not you?
Yes. But it's not fitted then.
But this is PDF or not?
No.
Just it's PDF.
Yeah.
So, the next speaker, Diego Rojas, and he's going to talk on testing cosmic isotropy, model-independent Hubble maps.
Hello. First of all, I want to thank the organization for the invitation. First of all, I want to start by giving some motivations on the work I'm going to present. This is working, right? Yeah? Okay. So, we know the lambda CDM model provides a remarkable and successful framework for understanding the evolution of the later universe. However, as Professor Belten already told us, there are a lot of tensions that have been introduced using all the new data that has been generated over the last decades. So these tensions have motivated further scrutiny on the model and the assumptions, the fundamental assumptions that we used to in the lambda CM model. So one of the key assumptions that the lambda CM model has is the assumption of the cosmological principle. The cosmological principle says that the universe should look statistically homogeneous and isotropic on large scale. So the work I'm going to present aims to be a test on the cosmological principle of isotropy. As the title of the talk says, in a model-independent way, by employing what is called a cosmographic approach or a cosmographic expansion. So here we have Hubble maps, which are one of the most direct ways we have for testing isotropy through the angular dependence of the cosmological parameters. So I use these maps and I do a statistical significant test on them so I can gather some information about the cosmological parameters that we fit on the maps. So as I said, the test aims to be a model-independent test. So the model independence is achieved through the cosmographic expansion. Here we have the luminous distance expansion in power of redshift up to order of 2, and we see that in this expression we have two free parameters, the Hubble parameter and the Q0 deceleration parameter. So what this expansion allows us is to measure distances that are independent of the contents of the universe and its nature. So we use this to do the test, independent model test. So I'm going to do the test using the Pantone Plus dataset. It's already been shown in a lot of talks, so I'm not going to dive too deep into this data sample. But I have to mention that as I'm doing a cosmographic approach, I have to make a cutoff on the redshift sample up to 0.1, so I can truncate the series and obtain a good approximation. So this is effectively the sample we are working with. And basically, to compute the Hubble maps, I employ two techniques. The first one is called the Helbig pixelation scheme and the hemispheric comparison method. What I do is separate the celestial sphere into a lot of patches, and for each and every one of these patches, I define a symmetry axis that goes through the origin. Then I separate the celestial sphere into a northern and a southern hemisphere. Then I fit the parameters for each and every one of these northern and southern hemisphere, and basically as I fit the parameters across the celestial sphere, effectively I obtain what is called a Hubble map. And so in particular I have defined 3072 sky patches, which is consistent with the Helbig pixelation scheme for n side equals 16. So I fit the maps basically by minimizing the chi-square statistic. I have to mention that I'm using the data provided by the Schutz collaboration, which then I need to use the entire covariance matrix in the chi-statistic. So I also look for anomalies on the autocorrelations of the maps using a Darwin-Watson statistical test. And so, as I said, I compare the maps with synthetic data sets to gather information about the actual data. So the first synthetic data set that I'm going to use is a synthetic data set where I replace all of the original supernovae positions in the sky with an even distribution of supernovae. And the second one is a synthetic data set which is consistent with lambda CDM, where the distance modulus of the data is replaced by value drawn from a normal distribution, which is centered at the lambda CDM fiducial value, and the standard deviation is given by the original data uncertainty. So the results. First, as I said, I'm looking for anomalies using this Darwin-Watson statistical test, and I found that including super low redshift supernovae introduces a lot of positive autocorrelations to the fits. So I decided to leave the super low redshift sample out of the analysis, and I didn't mention, but basically what we are looking for is Darwin-Watson statistic to be closer to a value of 2. So, so including low redshift supernovae, super low redshift supernovae is really far away from 2. So we have a value under 1. So given the considerations of the Darwin-Watson statistical test, this is the maps we ended with. Here we have the maximum isotropy levels for the deceleration map and for the Hubble map. The maximum isotropy level is defined as the maximum difference that we find for all of the defined symmetry axes. So here's the comparison of the data with the synthetic data set, which is consistent with a lambda CDM scenario. And here we have data in red. We see a complete agreement between the data and the synthetic data set. So we have then the second synthetic data set, which where we see the significant tension between the data and the synthetic data set. This data set, I remind, it's a data set consistent with an even distribution of supernovae in the sky. So we see this tension, which is well over the 95 consistent level. So these are both of the synthetic data sets plot together. So we see the tension with the set that is consistent with the even distribution supernovae, and so this is an overview of the results of the comparison between the Hubble maps and the synthetic data sets. We have that for both the Hubble maps and the Q maps, the p-value, which accounts for the number of repetitions that have a value higher than the maximum isotopies that we're measuring. Then we have a value of 0.4 for both the Q map and for the Hubble map. So we found that we can conclude from these results that the high anisotropy levels that we are observing from the data are an artifact generated by the non-even distribution of the data. So this method provides evidence for the cosmological principle of isotropy. So we have that the tension between the synthetic data set, it's over the 3 sigma. So I think it's a remarkable result and evidence for the cosmological principle. So I think that's all I had to say. So thank you for your attention.
Thank you very much.
Okay.
So, questions or comments? Can I ask you something?
Yeah.
This is a very nice idea. However, this is what we're discussing with Susanna in the morning. It's the following, that the real data, usually they accept homogeneity and isotropy.
Yeah.
So all the calibrations that you are doing when you are going to use the supernovae or whatever you want, inside there it's hidden isotropy, always. So the question is, in principle, if you want to check an isotropy, you need to go back and calibrate all the observational procedure again. So this is my question. Have you considered this possible complexity there?
In fact, even when I consider a synthetic data set that considers an even distribution of supernovae in the sky, we also observe anisotropies. The anisotropies are not does not vanish. So all the anisotropies.
No, I agree with that. I totally agree. And what I'm saying is that the people that are measuring supernovae, they assume isotropy.
Yeah, right.
So all the results, they have hidden isotropy inside.
Yeah,
so
we observe anisotropies because of the samples that we're using. In fact, use some of the, I think 1/3 of the data, it's under the transition scale, under the 100 megaparsecs. So in fact, we expect to observe some anisotropies from the data.
Very good.
Okay.
Any other question or comment? Okay, if not, let's thank the speaker again. So, very good. So now let's go to the last speaker of this section, which is Francisco Lobo. He will talk online. So Francisco, can you hear us?
Yes, I can hear you. Can you hear me as well?
Perfect. Yeah. So can you share your screen?
Sure. Can you see my screen?
Yeah, perfect. We can see your screen.
Okay, great.
And we can see. Okay, very good. Okay. So, Professor Lobo is going to talk on hybrid metric Palatini gravity, astrophysical and cosmological applications. So, Francisco, the floor is yours.
Okay, thank you very much, Manuel. Can you hear me well? Yes?
Yeah.
Can you hear me? Yes? Okay, great. So, thank you very much, Emmanuel. First of all, I'd like to thank the organizers for the very kind invitation to give a talk here. I would love to be there personally. It seems that there's many friends and great names and great talks. So it's a pity that I cannot be there personally, but anyway, this is the advantage of giving a talk in modern times. It can be done online, right? So like Emmanuel mentioned, I'm going to speak about a specific modified theory of gravity, the hybrid metric Palatini theory, and I'll be speaking a bit about the cosmological implications and also several astrophysical ones, okay, and also the viability of these theories. So anyway, so I'll just go ahead. Well, the question, is there a need for new gravitational physics, right? And I'll be speaking a bit about it as well. So this is just a brief outline of the talk, okay? And when you talk about going into new gravitational physics, it's always important to speak about the foundations of gravitational theories, okay? And so essentially, I'll be speaking a bit about, well, like I mentioned, a specific modified theory of gravity going beyond Einstein's GR, especially extension of F of R gravity and some applications. And like I mentioned, the theory that I'll be speaking about in more detail is the hybrid metric Palatini theory, okay? There's so many theories out there, and I'm sure that you heard a few of them in the conference. I'll be speaking a bit about this one because it's quite pedagogical. in all aspects, especially when you go into the foundations of these theories and also the approaches that exist. So I think that this hybrid metric quality theory is very pedagogical because it takes into account most of the approaches. And like I mentioned also, in the title, I'll be speaking a bit about the astrophysical and cosmological applications. And as one now has a new block, a new fundamental block to build these theories, it's also very important to try to investigate and explore their viability, okay? And in that context, I'll be speaking a bit about the graviton propagator to see exactly the viability and the plausibility of these theories in terms of stability, in terms of ghosts that may appear and all that. And then also some future research, okay? So we know that the late-time cosmic acceleration has posed great challenges, right, to the gravitational theories, and it does pose the question that is GR the correct relativistic theory of gravitation? So that is the big question, in fact, you know. And as GR is facing so many challenges, specifically its difficulty in explaining particular observations like the late-time cosmic acceleration, and also the incompatibility with other well-established theories like quantum mechanics, and also the lack of uniqueness, right? Because there's so many theories out there that explain and that take into account the phenomenology that GR takes into account. So is this indicative of a need for new gravitational physics? Okay, so that is a big question. And of course, cosmology is the ideal testing ground for GR, okay? In particular, the late-time cosmic acceleration. And now that we have the Euclid flying, that'll be fantastic because it should restrict many, many models that exist out there. I'll be speaking about that later as well. Anyway, so there's the promising approach is that we assume that at large scales, GR breaks down, this in modified gravity, and that a more general action does indeed describe the gravitational field, okay? And one can take into account so many generalizations of the Einstein-Hilbert-Lagrangian. F of R gravity is one of the most popular ones. It also depends on the scale, right, that you take into account, that you're exploring. Well, for instance, if you want to explore the early universe, then one has very strong curvatures. It's very useful to use an addition to the Einstein-Hilbert action or gravitational Lagrangian, the R squared term, where R is the scalar curvature, where you have strong curvatures. So that term R squared dominates. And if you want to take into account the late-time cosmic acceleration, then you take into account something like 1 over R, where one has low curvatures and that term dominates. And then one can also play around with this, okay? One can consider, well, so many invariants like the contraction of the Ricci, the Riemann, and all the combinations that one can take into account, F of G, Gauss-Bonnet, etc. There's so many models out there, okay? And in fact, the physical motivations for these modifications of gravity, may reside on the possibility of a more realistic representation of the gravitational field near curvature singularities, and also to create some first-order approximation for the quantum theory of gravitational fields. Let me just go on into the foundations, into the applications of this. So GR is a classical theory, right? So one may argue that there's no reference, that's a reference to an action is not needed. But in fact, the Lagrangian formalism is extremely elegant and it has great merits. For instance, at the quantum level, the action acquires a physical meaning, and a more fundamental theory of gravity will provide an effective gravitational action at a more suitable limit. It's also very easier to compare alternative gravitational theories through the actions than by the field equations. As you well know, the field equations are extremely messy, right? So it's at the level of the action, at the Lagrangian, that one has a better grasp of the physics. As described in terms of coupling, the kinetic terms, the dynamical terms. So it's here at this level that it's much easier to have a grasp of the physics. So when you go into these gravitational theories, it's very important to speak about the foundations, okay? And this is extremely difficult. So I'd like to mention that back in the 50s and 60s, Chief and Dickey mentioned that the gravitational experiments do not necessarily test GR or in fact any gravitational physics. They don't test the validity equations. These experiments that they were conducting back then test the validity of principles, okay? And this triggered a lot of research into the development of powerful tools for trying to discriminate in all these theories that exist back then, okay? And one can mention the so-called PPN expansion, the parameterized post-Newtonian expansion, which was pioneered by Nordtvedt and then also by Will and Nordtvedt himself. So indeed, that's the idea that experiments test principles and not specific theories implies the need for exploring the conceptual basis of a gravitational theory. And one can take into account a very nice framework, which is the Dickey framework, which is probably the most unbiased assumption to start with when you develop a gravitational theory, that one considers that space-time is a four-dimensional manifold, with each point in the manifold corresponding to a physical event. Note that here the metric and the connection is not necessarily, okay, at this stage when you're constructing your gravitational theories. And the equations of gravity and the mathematical entities in them are to be expressed in a form that is independent of the coordinates. So in fact, in a covariant form, okay? And it's also very common to think of GR, or in fact any other gravitational theory, as a set of equations or an action. But it's also very important to mention that a complete and coherent axiomatic formulation of GR, or in fact any gravitational theory, is still lacking. So one needs to formulate principles, okay? And in fact, one important one is the covariance principle, which is present in the Dickey framework. So it's very important when you start thinking about these gravitational theories to have some guidelines, and that's extremely difficult to have, okay? One guideline is in fact the Einstein equivalence principle, okay? And this does restrict your theories. And in fact, the Einstein equivalence principle is at the heart of gravitational theory. And if the Einstein equivalence principle is valid, then gravitational must be a curved space-time phenomenon. That is, it must obey the postulates of metric theories of gravity. That is, space-time is endowed with the metric. It possesses a second-rank non-degenerate tensor. The whirl lines of test bodies are geodesics of that metric. And also in local freely falling frames, Lorentz frames, the non-gravitational laws of physics are those of special relativity. So if you want to take into account that one of the guidelines for constructing one of your gravitational theory is the Einstein equivalence principle, it does rule out many models, okay? Anyway, so I'll go on to the approaches. So, for instance, F about gravity, okay? It's one of the most simple approaches to modify gravity. What you do is just generalize the Einstein-Hilbert action by taking into account a function of the scalar curvature. It's got extremely appealing features. It combines a mathematical simplicity and a fair amount of generality, okay? But here, if you take into account your field equations, in fact, the trace of your field equations, you see that it is a dynamical degree of freedom, okay? And this does introduce a light scalar degree of freedom, which doesn't, in fact, produce the late-time cosmic acceleration, but it strongly violates local tests, okay? Local constraints. And this was a big issue back. If these people in the audience that were working on this back in 2006, 2007, 2008, that's that era, this was really intriguing, right? Because to the past, you have to take into account the PPN perimeter, right? The gamma perimeter. For instance, we know that gamma is equal to 1. And back then, if you recall, there was these papers, and very solid papers where in fact there was no mistakes done, right? where the authors demonstrated that the gamma perimeter was equal to 1/2, and they argued that F of R gravity was ruled out. And then the following week, there was another paper, apparently with no errors, which stated that gamma was 1, okay, equal to 1. And this continued for a few weeks, and in fact, a few months, okay. Only a bit later did we find out that it was discovered, right, that the way out was through the so-called chameleon mechanism, okay? So the scalar field becomes massive in a high-density background, okay? And one can argue, I mean, it also depends on your point of view, okay? One can argue that the chameleon mechanism is quite contrived, okay? And other people, the other class of researchers mentioned that there's no problem, but in fact, it's a problem, okay, with F of R gravity. So F of R gravity is only valid, okay, if the so-called chameleon mechanism holds, okay. So in fact, when you do research in modified gravity, there's several approaches. There's a metric approach, where you first consider that the fundamental field is the metric, okay, and you vary your action with respect, to the metric. You find your field equations, which describes your dynamics, and you work out all your system and all your predictions, and you play around with your models, okay. There's also the so-called Palatini formalism, okay, where you take into account that there's another fundamental field, which is the affine perimeter, the connection, which one can also argue that the connection is probably more fundamental than the metric, okay? So if you consider that your gravitational action also depends on this connection, where your method Lagrangian given by equation 2, this part of here, I don't know if you can see my cursor, but if your method Lagrangian is only dependent on your metric, then you have the so-called Palatini approach, okay? If you take into account that your method Lagrangian also is a function, or also depends on your affine connection, then you have the so-called metric affine formalism, okay? So you have essentially these three approaches to gravitational theories. I would argue that there's also another approach, okay? So we started working on this approach back in 2012, I think, 2011. And so this is a theory that I want to speak about. So it's the so-called hybrid metric Palatini formalism. So both approaches, the metric and the Palatini formalism, one can argue have some drawbacks, okay? So our motivation back then in 2011 was trying to figure out a different approach, trying to combine a hybrid approach where one has two fundamental fields, okay? You have the metric and also the Palatini, the metric approach and the Palatini approach. So what we did was just consider the action that's given in equation 3, okay? So we know that GR works very well, right? Of course, it's got all those problems which I mentioned in the beginning. But if you kind of consider a sort of perturbation to the Einstein field equation, to your Einstein-Hilbert Lagrangian, by considering a new function, okay? So this R, this standard R, is the metric Einstein-Hilbert curvature scalar, and this curly R over here, okay, is a new Ricci is a new scalar curvature, which is defined in terms of a new independent connection, okay, which is given by this definition over here, okay. So what we take into account is that we define a new affine connection, okay, and we have this gravitational action. And what you do now is you work out your field equations by varying this action with respect, to the metric and then also to this new connection. And back then in 2012, it was very exciting because we found some new issues and new aspects of the theory, which was promising, which really spurred us to work much more on this theory. So to give you a feel for the equation, so if you vary your action 3, with respect to the metric, you have this gravitational field equation, given by equation 4, which is very similar to the Palatini formalism, but it's a bit different in fact, you know. And of course, we define the energy momentum tensor as usual by equation 5. And now, when you vary your action with respect to this new connection, you have this equation of motion for this quantity, okay? Which, in fact, is an equation of motion for the connection. So this tells you that this independent connection, okay, is the Levi-Civita connection of a new auxiliary metric, which we define by age, okay? And it's given in terms of the physical metric in the sense that it's the Matter-Lagrangian couples to this, and there's also a conformal factor, which is given by this large F, which is defined in terms of the derivative of the Palatini curvature scalar, in terms of with respect, to itself. Okay, so one can play around with these field equations, of course, but in fact, it's much easier to work out the scalar tensor representation, okay? So what we did was find a new equivalent scalar tensor representation, and those of you working with the so-called Palatini formalism will say, oh, but that's very similar to the Palatini scalar tensor representation. Indeed, it is, but there's a factor here which varies, okay? So if you well, those of you working with f of r gravity know this. Well, just for those of you who aren't familiar, the metric approach to f of r gravity is equivalent to a scalar tensor theory, a Bronsted theory, where your omega, where your Bronsted perimeter is equal to 0, okay? For the Palatini formalism, it's also equal to a Bronsted scalar tensor theory, where your Bronsted perimeter is equal to -3/2, okay? So this is very similar to the Bronsted in the Palatini formalism, but the coupling to R is different, okay? In the Palatini formalism, you only have the scalar field coupled to R. So this is a different theory to the Palatini formalism in the scalar tensor representation. And this coupling over here makes all the difference, all right? And so if you now, one has now this gravitational action, and if you vary with respect to the metric, you have this more involved gravitational field equation, which is also very similar to your Bronsted one, but it also varies with respect to the coupling here, okay? And so over here, it's transparent that space-time curvature is generated both by the matter and also by the scalar field. If you also prefer in working in the Einstein frame, that's fine as well. So what you do is just consider a conformal transformation given by equation 9, and then you see that the Einstein frame Lagrangian takes the form of equation 10, okay? So this is also quite pedagogical if you prefer working in the Einstein frame. But you have to be careful as well with all the problems associated with these transformations, going from the Jordan frame to the Einstein frame and then vice versa. And of course, this can also be put into the canonical form by introducing a new rescaled field, okay? And so it's very important also to mention that the vacuum theory then becomes a canonical scalar theory with a very specific potential, okay? And this stems from the specific form of your f of r, of your Palatini scalar curvature in the Einstein frame, of course. Okay, so let's just work on. So if you also in terms of being pedagogical, when you have a new gravitational theory, you have to test it at different scales, right? For local tests, for cosmology, and if you also wish at the intermediate scales, right? For galaxies in terms of dark matter. So what's one has to do first is see what the theory predicts for the weak field and non-relativistic velocity behavior. Okay, so for weak fields, so it's quite easy. It's quite straightforward to find that the effective Newtonian constant is given by the equation 12, okay, and also the gamma is also given by equation 13. So note that gamma must be equal to 1, okay? So this ppn perimeter must be equal to 1. So the question is, how do you make this equal to 1? Well, one can have a large mass, okay, which is what is done in f of r gravity, which I will show you in a while. But even if the mass is very light, so it does explain the late time cosmic acceleration. But if your background field is very small, okay, then one can consider that the gamma is equal to 1, irrespective of the mass, okay. And this is very important because to have a comparison, let me show you what happens in F of R gravity, okay? In F of R gravity, here's the gamma term, okay? So gamma must be equal to 1, and here, there's only one mechanism to have this, is when the mass is very massive, okay? So that's exactly what we have for the so-called chameleon mechanism. So your mass gains, becomes heavy with the local, or the background densities, okay? So here, note that one can evade, with the hybrid metropolitan theory, one can evade the so-called chameleon mechanism. So we don't really need the chameleon mechanism in the hybrid theory. So when we first discovered this, this was the real motivation to go further into the theory, because one can really evade, once again, the so-called chameleon mechanism. And that is really great to know, because we weren't very fond of the chameleon mechanism. Also, that also depends on your point of view, okay, and your. So to show you what happens now in cosmology. So for instance, let's have a look at what happens for the late-time cosmic acceleration. So consider a flat Friedmann-Robertson metric Walker metric given by this here. Your modified Friedmann equations are given by these equations 17 and 18. This is just to give you a feeling, okay? So it's very similar to what happens in the Palatini formalism again. But this factor over here, this factor that appears in the denominator makes all the difference, of course, And we also have here the modified Klein-Gordon equation that gives you the evolution of the scalar field. Okay, that's just for you to see exactly, if you're aware of the Friedmann equations in cosmology, what we have here difference. Okay, so let's see exactly how one can construct a very nice model that explains the late-time cosmic acceleration, and that also takes into account the local tests, okay? So if you consider, for simplicity, a quadratic potential, there we are, well, given by equation 20, and the trace of your field equation gives you this equation over here, this trace equation, and with cosmic expansion, we see that the trace of the energy moment intensity goes to 0. So it naturally evolves into a de Sitter phase, okay, where your V0 will be proportional to your lambda, okay? So this is also consistent with observations, okay? Now, if V1 is positive, okay, we see that the de Sitter regime also represents the minimum of the potential, and the effective mass for local test is given by this equation here, and it's positive if we have this condition. Okay, now if V1 is much larger than V0, then the amplitude is small enough to pass the solar system test, local tests. So in fact, we see that the exact de Sitter solution is compatible with the dynamics of the scalar field in this model. And this is really great, okay? So a very simple model with a quadratic potential gives you exactly, passes both scales, local scales and also large scales in cosmology. And of course, we have much more work on this. We have many more cosmological models and more evolved ones than this quadratic one. But this shows you with a simple model how one can construct a viable model that passes both tests, okay? Now, if you, as this is a cosmological conference, I'd also like to see exactly, to show you what happens with the cosmological perturbations, vacuum fluctuations, how one can explain the large scale structure of the universe, okay? So to really understand the cosmological structure formation, we have to deduce the perturbation equations and then also analyze them for specific cases. And this does pave the way for a detailed comparison of the predictions for the cosmological data on large scale structure and the cosmological background. This will be, very important for data coming in from the Euclid mission. So if you consider the so-called Newtonian gauge, where one has two gravitational potentials, okay, given by equation 21, and if you consider a matter source is a perfect fluid, we have the background equation of state and the density perturbation, given by these definitions here. Once again, I don't know if you can see my cursor. And we also have the pressure perturbation and the velocity perturbation, and we can show that the gravitational potential is given in terms of the scalar field in your specific theory, okay? And of course, if you are assuming the perfect fluid, like I mentioned at the beginning, one can work out the circle continuity and the Euler equations for the matter component, which are given by equations 23, 24, and the linear part of the Klein-Gordon equation is given by equation 25. Also to give you a comparison of these equations that are worked out in the hybrid theory with what you know, okay? And of course, if you want to work out the matter-dominated cosmology, we consider formation of structure in the matter-dominated universe, okay, by assuming scales deep inside the Hubble radius, which is the so-called quasi-static approximation, and we work out the continuity and the Euler equations given by equation 26, where the effective Newtonian potential is given by equation 27, okay, which is very similar to what we had previously. So equation 26 also provides a very simple approximation to track the growth of structure within the linear regime during the matter-dominated cosmology. And much work has been done here in the past, and models have been constructed that are consistent with observations, okay? So here we are once again. It's very important to have confrontations of specific model predictions with the present large-scale structure and forecasts for the constraints from future experiments. In fact, from present experiments, which is the Euclid mission, which has been already sending many great images. Okay. What about vacuum fluctuations? So it's also important to study the propagation of the scalar degree of freedom in vacuum. This is also very important to check consistency your theory. So if you consider vacuum, of course, we have the curvature perturbation is given in terms of the Newtonian gauge, well, given by equation 28, and we obtain, once again, the exact linear evolution equation, which is very tedious to arrive at, and this can be used to study the generation of fluctuations. Not much work has been done here due to the very messy equations, but in fact, I think that a lot of work can still be done here in the sense. Okay, of course over here it should be easier to work with your Einstein frame, but we haven't done that yet. So this is still work open. Okay, if there are people in the audience who want to try their luck with this, please do let me know. Anyway, here we are with a new theory where we have a new building block, okay? So this hybrid theory space is really large, okay? Because in addition to the metric, okay, we have this new connection, okay, which is independent of the Levi-Civita in terms of the physical metric, okay? So one can also construct many different invariants. For instance, one can use now this new building block, okay, and construct invariants in terms of hybrid mixtures, okay, of the curvature Ricci tensor, for instance, of the metric Palatini Ricci curvature. One can consider now a whole plethora of mixed terms, okay? And instead of trying to tackle this by brute force, it's very important to see exactly how one can test the viability of these new theories, okay? We started working on this, but it was so messy. But there's quite a simple way in fact, to see exactly which are the viable higher order terms or higher order theories that appear in the more general hybrid metric Palatini theories. Okay, so let me give you an example. So if you consider this action, so we have this function, this hybrid function, okay, where you have the metric curvature. You have the Palatini curvature, and then you have this new quantity which is constructed in terms of a hybrid metric and Palatini Ricci tensors. Okay, so this is quite pedagogical to see exactly what happens here, and the equations are extremely messy, but you have here the field equations. Okay, where these terms with the indices denotes derivatives with respect to the quantity involved. And the equation of motion for the connection, so you take this and then you vary your action with the connection, and then you see that it's, the new connection is a Leibniz connection of a new auxiliary metric, which we define as this hats G mu, okay, which is given in terms of this combination, okay, or given by equation 32, which is very messy in fact. Okay, now of course one can play around with this and one can use the standards, I mean, one can do whatever you want. I mean, use the theory to show what the weak field limit gives you, what the cosmology is. But it's also quite pedagogical to take into account the graviton propagator, okay, to see exactly the stability or instability is present in these different theories, okay? So if we consider perturbations around Minkowski space, okay, and then you invert your linearized field equations for the physical metric, this provides the propagators for the graviton and the additional degrees of freedom that may be present in these perturbations, okay? So recall that the propagator is defined in terms of equation 32. With this quantity over here, this tail, is the linearized energy momentum source, okay? So in the formalism of the spin projector operators, this result can be given in Fourier space, okay, in terms of two functions, A and C, okay? I'll show you in a while in the next slide what this A and C is. But note that this propagator, this operator, picks up the spin 2 scalar, mode of the fluctuations, here it is, and then also the scalar mode, okay, so over here. So this is also very, very pedagogical, because now if you have, well, first of all, let me show you what the A and C is defined in terms of. Here we are, A and C. We have these definitions where this capital A and capital B are given in terms of the specific forms of your F that you may construct, okay? So if you can now, let me show you exactly what to do with specific models. So for instance, take into account F of R gravity, the pure F of R gravity, okay? Where your propagator is given by equation 38. Here we have the GR term. And then over here, we see that this picks up an extra scalar degree of freedom. And that should be expected, because F of R models are known to be equivalent in the metric formalism to a Brans-Dicke theory with a vanishing perimeter, okay? So this we know, in fact, you know, and the mass of the scalaron is given by this quantity over here. And as long as the second derivative of the F of R is non-negative, the theory is stable. So we already knew this, okay, from the stability issues that were explored back in 2006, 2007. So over here, it's consistent, okay? So over here, we have this consistency test to see if our approach is valid or not, okay? In fact, if this is not non-negative, then this picks up a tachyonic degree of freedom, which spoils the stability around Minkowski space. So it's intuitive that this thing does function for the pure model. What happens, for instance, in F of R gravity in the Palatini formalism? Okay, so we know, like I mentioned at the beginning, that the Palatini formalism is equivalent to a Brans-Dicke theory, with the perimeter is equal to minus 3 halves. And we also know that this particular value also corresponds to a vanishing kinetic term of the field, which is non-dynamical. Therefore, we should expect that no additional scalar degree of freedom should appear. And when you take into account all the formalism that was worked with the graviton propagator approach, we do in fact see that it's exactly the same as we have in GR, as was to be expected. Okay. What happens with the hybrid metric Palatini theory that I was telling you about? Also intuitively, so we know that in Ricci flat spacetimes, the hybrid metric Palatini theory shares the property of the Palatini F of R theory, which in vacuum reduces to GR with a possible lambda. Okay, so we should expect the same behavior as in the Palatini formalism, and that's exactly what we have, working out all the formalism. So it's no surprise that no new propagating degree of freedom in Minkowski spacetime does appear, which is fantastic. Okay, so that linear theory that I was showing you at the beginning is also well consistent to all the gravitational wave behavior that is present also in GR. Okay. Now, also in terms of pedagogical terms. Okay. So if you consider that now your theory depends on your Palatini invariant, okay, and this quantity over here, which is defined in terms of that quantity that I showed you at the beginning, we see that the propagator is given by equation 41. And we see that there's a lot of terms over here involved, okay? So we verified that this modulated graviton propagator adds 2 extra poles, okay? And therefore, Escalier propagator has 5 poles, in fact, okay? This theory should be transparent that it's seriously haunted by ghosts, and therefore it can be considered to be non-physical. And it's also easy to convince oneself that this occurs very generically once one builds actions from higher order curvature invariants, okay? So if you want to, so that's why probably it's not worth spending too much time and spending too much effort with these higher ordered theories because they are contaminated by these instabilities, okay? So what about at the intermediate level? I don't have time to speak about this. I don't know how much time I have, but I think that I should be near the end. But anyway, so with dark matter, we also worked out the intermediate scale, okay? And quite a lot of work was done over here, and also more recently, in fact. And we also found out that take into account different approaches to geometric effects at the level of the galactic scales, take into account the flat rotation curves, take into account the virial theorem approach. We also verified that one can also mimic dark matter using the hybrid metric Palatini theory with the perimeters that are consistent with local tests and also large-scale tests, which is very promising. I don't have time to speak about this, but here are the papers if you are interested in exploring this. Okay, some free publicity if you want to know more about these theories. There's a book out that came out in 2018. I'm going back to the future now. But all these theories, all the motivation and applications are worked out here. Recent work also, there's also much more recent work. We also worked with cosmic strings, with vacuum solutions, with star-like solutions. The weak field with a more generalized hybrid theory was also worked out. Sudden singularities and also the dynamics in the cosmological phase space of generalized hybrid metric Palatini theories, which are also consistent, which are also viable, in fact, So quite a lot of work was done over here. Okay, so to wrap up and to conclude, so I'd like to mention that we presented a hybrid metric Palatini framework for theories of gravity, and we tested the new theories that it entails using a number of checks and observational constraints, okay? Very important, in my opinion, is that this may evade altogether the so-called chameleon mechanism. It doesn't evade the symmetron mechanism, okay? But it does evade the chameleon mechanism, okay? One excludes theories also inhabited by ghost-like and superluminally propagated and otherwise pathological degrees of freedom. We saw that these higher order terms are certainly contaminated with these instabilities. One can also work out specific theories where one can find which may evade these instabilities. This has not been done, okay? But it's quite messy, in fact. But it's also quite important to mention that in a monastic view of physics, one would expect nature to make somehow a choice between 2 distinct possibilities offered by the metric and the Palatini formalisms, okay? We've shown that there's a theory that is consistent with observations that combine the elements of these 2 approaches, and this is possible, okay? Hence, gravity admits a diffuse formulation where mixed features of both formalisms are successful to address a large class of phenomena, okay? And to really, finish off, It's important also to mention that tests from the solar system, the large-scale structure, and lensing essentially restricted the range of the allowed modified theories. And surveys, as all these that I mentioned here, the Euclid, SKA, DES, EBOS, STS, will provide new opportunities to test the different models involved in cosmology. And of course, for the new generation, I mean, it's really fantastic that we have this wealth of unprecedented high-precision observational data that will become available by these upcoming and planned surveys. So one may say that we are dawning. In fact, we are already in the golden age of cosmology, which offers a window into understanding the nature of the late-time cosmic acceleration, dark matter, and of course of gravity itself. Okay? So thank you very much for your time and attention.
Thank you very much, Francisco, for this enlightening talk. So, we have time for questions or comments.
Hello. Can you hear me?
Yes, I can hear you.
Okay, thank you very much for the nice talk. I have a question regarding the chameleon and symmetron mechanism. What would be the advantage of evading the chameleon mechanism if you still need the symmetron mechanism for the theory to meet the solar system constraints?
Yeah, well, that's a very good question, okay? So it does at least the chameleon mechanism, okay? So in that sense, I mean, that's a very positive aspect. And in fact, it doesn't solve the symmetron mechanism, okay? So that's also a shortcoming. I don't really know exactly how to answer the question. We haven't really worked on it, to try to solve the problem. But in fact, it doesn't evade the symmetron mechanism, okay? But that's a very good question.
Okay, thank you.
Any other question? Hi, thank you for your nice talk. I want to ask you about, I don't know anything about this, I think so, just a little bit. Can you explain me the difference between Palatini formalism and the hybrid, Palatini formalism, please? Thank you.
Yeah, sure. So let me just go back to, oops, for some reason I can't go back. I don't know why I can't go back to my slides. Okay. Maybe if I put it, yeah, okay. So, right to the beginning. Can you see my slides? Yeah?
Yes.
Yeah? Okay. So it will probably be, well, okay. Equation 2, okay? So equation 2, you have equal form, okay? So if you consider that you take into account the metric formalism, it's simple. That R there is the standard metric curvature scale, right? Now, one can also consider that this RV here, okay, using this action, okay, you can take into account the Palatini formalism, okay? When you take this action, and then you vary with respect to your metric and your connection. So that is the Palatini formalism, okay? Take into account this action. What we do is, in the hybrid theory, is we keep the Einstein limiter. One can also have two functions here, like the f of r metric or r Palatini. So over here we have the standard Einstein Hilbert action, okay, or Lagrangian, built in terms of your metric. Okay, only on metric. So this here, depends only on your metric. And over here, we add a new term, okay, it's defined in terms of a new independent connection. Okay, so it does differ substantially in the so-called Palatini formalism by adding to your Lagrangian these two quantities, okay? And then you vary your action with respect to the metric. this action, and then you get your Einstein equation plus something else, okay? And then you also vary this action with respect to your new connection, and you have a different orthogonal equation, which is given by this thing over here, okay? So in fact, it does differ from the Palatini formalism in this respect. Where at the action, so that's what I was saying at the beginning, it's very useful if you want to build a gravitational theory to start from the action, okay? And then start with the fundamentals, and then you change, you play around with your action, okay? I don't know if I answered your question.
Yes.
Hello, Professor. I have another question. Could you tell us something about the shortcomings of the Palatini formalism or formulation?
Yeah, sure. I don't think, well, I don't think there's many shortcomings, okay? Because this was I mean, I think one should have a historical session on this, okay? Because back in 2009, 2010, 11, people didn't like the so-called Palatini formalisms, because big names were advocating that they were riddled with shortcomings, okay? For instance, there was the singularities at surfaces, you know, that had to do with your equational state, you know. So what propagated was that the Palatini formalism had severe drawbacks, okay? And now we know that it's not like that, okay? One can evade these nice papers. I mean, there's a very nice paper that I can indicate you to, where it's by Gonzalo Olmo. It's the review of the Palatini formalism. You can see it on the, it's a paper that came out in 2011, where he explains it more specifically. So now we know that these so-called singularities is not problematic, okay? I think that the problematic issues come from the metric formalism with the so-called comedian mechanisms, okay? With the so-called Palatini formalism, it's also quite historical that a lot of research was not done in those years due to this erroneous consideration that the Palatini formalism was not viable, okay? Now we know that it doesn't consist of any severe drawbacks, okay? And I think that's also very pedagogical of how these theories evolve, how they do how it's propagated, you know, and anyway. I could say much more about this, but I won't stop talking.
Very good. Hello, hi. Thanks very much for the talk. I was interested in what you were saying about how you could use these theories also to explain dark matter phenomenology. Do you know, I mean, is it possible to basically match with CMB constraints and as well as small-scale galaxy constraints with these theories?
That's a good question. The CMB, I think some work has been done there. I mean, there's been a lot of criticism, all right, with explaining dark matter with modified gravity, and people take into account the phenomena like the bullet cluster, you know, that there's gas which passes through, which cannot be explained by modified gravity. On the contrary, it can, okay? I mean, there's no convincing paper that does explain that. It's very problematic also with the CMB, okay? But also, there's papers that have been done there, where you have these extra terms which also mimic these gravitational potentials, okay? Same thing applies also with the flat rotation curves, okay? So when you play around with your field equations, you find that you have these extra terms, okay? And these extra terms also play the role of an effective dark matter component, okay? So in fact, one can fine-tune, of course, it's fine-tuned. One can also fit these flat rotation curves. That's been done also with F gravity, for instance, back in 2002, I think the first papers that came out back then was by a team from Salvatore Capoziello and his collaborators, and then much work was done there in other modified theories of gravity. So what we did over here was something very similar. We also worked out the so-called virial theorem, where you have this extra mass, this missing mass that what comes in, and this extra mass can also be accounted for by these extra gravitational terms, higher order terms, okay, which also mimic kind of dark matter. So in that sense, I mean, one can also find two schools, okay? A school which defends dark matter as a particle, you know, as a field, whatever. But in fact, then it's never been detected, you know. And there's a school also which advocates and also defends that it's dark matter. These gravitational effects, you know, that we observe, you know, are by slight modifications of gravity. What is also quite pedagogical is that if you take into account, well, think about it. For instance, at the galaxy level, okay. So one needs. So if you consider a power law of F of R gravity, for instance, here we have this thing over here, this action. If you consider a power law where you have, for instance, R to the power of 1 plus a very small component, so slight deviations. So if you intuitively try to build a model that slightly deviates, okay, from GR, this new parameter can also be constrained by the observations, okay, and that's also been shown to be the case. So one can build these models that mimic these flat rotation curves. Anyway, I mean, it also depends on your point of view. It depends on your taste of models. If you don't like modified gravity, then sure, go ahead with dark matter. You know, dark matter as a particle. But then you'll be confronted with a mantra that appears in all these conferences. That's from experiments. You know, that's no excess has been detected, no dark matter particle has been detected. You know. Anyway, it's even if one does rule out modified gravity as dark matter, as a geometric effect, of course, you know, it's been very interesting. It's been very pedagogical to understand the mechanisms involved here, and I don't think that there's a very definite answer to your question.
And Francisco, for the last question, what about the matter coupling in this series? Because in principle, you have a richer possibility here to couple matter with geometry, right? So, for instance, the last term in action 2, there is a standard one, but here you could have matter couplings depending on the connections, right?
Yes, exactly. So if you take into account the so-called metric affine formalism, here again, it also depends on the way that you classify these theories, okay? The so-called metric affine formalism is when your matter also couples to this connection, okay? So that's very important if you take into account fermions, okay? So that will also give you some extra terms, all right, that one can play around with, which is not really relevant in cosmology, but should be very relevant if you take into account high energy phenomena, okay? I think there's some papers that have been working around with that back in the, I don't know, 2010, 2011. I think that, I can't remember now the authors, but work has been done there. But that's also a very good question, exactly.
Very good. So is there anything else? If not, let's thank the speaker again.
Thank you very much.
Thank you, Francisco. And let's go for lunch.
I'm going for supper now.
Thank you very much, Professor. Please, after the lunch, we have Professor David Vance, and then now we go to lunch, please. Thank you very much, Professor. It is connecting now, I think.
Thank you very much, Giovanni. Thank you very much. Okay, I don't know if you can still hear me.
Yes. See you.
Thank you. Bye-bye, thank you.
Yeah, thank you very much. Bye-bye.
After in the end, at the very end.
To buy some things from the supermarket, my kids. And then I will come back, but when you will be where for lunch?
You are going to lunch there?
No, I mean, we go to the supermarket to buy some things.
Okay.
You have to see our last paper with Bisaos, exactly, non-Gaussian, exactly what you saw, non-Gaussian, Google that, I mean,
Right now.
yeah. So I will go there, and then just send me a message where you are, and I can join you. Good, if I have it. Good.
¿Me puede filmar la asistencia allá?
Ah, yes. I know that. But I think it's in the other.
Ahí está.
Ah, yeah.
Gracias.
Anyway, see this paper and you can see exactly yes, the non-Gaussian effects.
What model are you considering?
No, yeah, but the model is kind of way. So if you have non-Gaussian, there's no way. Yeah, because this is what you are going to see in media or
like these plots here.
Yes, exactly.
Yeah, I want to find the time to
And also you need what you have to take into account is the following. If the pH density is big enough, then you can say it's the universe of the background. And you can have a swimming pool as every matter. So before the radiation, you have a window with pH dominant, and then the universe at the background. It doesn't matter. So you know, this is the damage of the background, whether matter or radiation, plays a role in the transfer function of someone else. Good. Okay.
we should